In the cosmic silence beyond the Milky Way, something flared into brilliance, briefly, but powerfully enough to draw the gaze of astronomers across Earth. This wasn't just any light. It came from a star not even born in our galaxy. It came from a star that lives in the outskirts of another galaxy entirely, R71, a volatile, luminous blue giant perched on the edge of destruction. But before we continue, subscribe to the channel so you don't miss out on any of these videos. R71 exists in the Large Magellanic Cloud, LMC, a satellite galaxy of the Milky Way. To call it a neighbor may seem generous, given that it's located roughly 160,000 light-years away. But in galactic terms, that's close enough that we can study its stars in surprising detail, but far enough that the light we see now began its journey when early humans were still discovering fire. That's how far into the past we must look to witness the present state of this star. And what a star it is! Most stars we observe in death belong to the Milky Way. They're within a few thousand light-years, embedded in the same spiral arms that cradle our own solar system. R71, however, is different. It is an outsider. It exists not only in a different place, but possibly under different physical conditions, forged in an environment less enriched with heavy elements than our own galaxy. This makes it a unique probe into the life cycles of massive stars formed in low-metallicity regions, offering a glimpse into stellar behavior that may echo the early universe more than modern times. When R71 flared in 2012, its sudden brightening jolted the astronomy community, not just because of the sheer intensity of the outburst, but because it was happening far outside the bounds of our galaxy. To shine so brightly across 160,000 light-years is to possess nearly incomprehensible luminosity. It didn't just flicker like a nearby variable star, it burned like a cosmic beacon, forcing us to pay attention. But even before the eruption, R71 was known as an enigmatic object. Variable, massive, and mysterious, it had been on watch lists for decades. Its changes in brightness and spectrum made it an object of fascination. But it was that 2012 event, a luminous eruption seen across the intergalactic void, that pushed it into the spotlight. For a while, it became one of the brightest stars in the entire LMC, reaching a magnitude that made it visible even through modest backyard telescopes. Here's what makes R71 even more extraordinary. While it belongs to a different galaxy, we can still observe it with high-resolution telescopes. Ground-based observatories in Chile, space telescopes like Hubble, and radio and X-ray telescopes have all contributed data. In this sense, R71 becomes a bridge, an object that links galaxies and helps us understand how massive stars evolve under different conditions than those in our Milky Way. But R71's story is not just about location. It's about potential. Massive stars don't live long, and they don't go quietly. R71 is nearing the end of its life. Whether it dies as a supernova, transitions into a Wolf-Rayet star, or collapses directly into a black hole, it offers an unfiltered window into the final stages of stellar evolution beyond our own galactic home. So, when we talk about R71, we're not just talking about a single star. We're talking about the power of stars to communicate across space, to tell stories written in light, shaped by gravity, and concluded in fire. And we're talking about one of the rare instances where the universe lets us watch from afar, as a giant slowly unravels. To understand the nature of R71, we have to peel back the layers of its identity. Because R71 is not just a star, it's a category-defying phenomenon. Astronomers have classified it as a luminous blue variable, or LBV for short. That term alone carries with it a universe of meaning, because LBVs are among the most unstable, unpredictable, and violently evolving stars known to science. They are not steady suns, glowing calmly for billions of years. They are cosmic time bombs, flickering and flaring as they stagger toward their inevitable end. LBVs are rare. They represent an extremely brief and volatile phase in the life of the most massive stars, stars that began their lives with at least 20 to 40 times the mass of our Sun, and sometimes far more. These giants live fast and die young. Most of their lives are spent fusing hydrogen into helium in their cores, but when that fuel is spent, things begin to unravel. And for some, before they even reach the cataclysmic finale of a supernova, they enter this strange, violent LBV phase. During this time, these stars become highly unstable. They can undergo massive outbursts, shedding enormous amounts of material into space, dimming or brightening by several magnitudes, and changing their physical appearance almost dramatically from one decade to the next. Their temperatures can shift. Their radii can balloon outward. And their luminosity, already millions of times greater than that of the Sun, can climb even higher, to the brink of the Eddington limit, where radiation pressure nearly overcomes gravity itself. At the heart of these changes is a battle between two forces, radiation and gravity. In most stars, gravity wins, pulling matter inward and allowing the core to burn in balance. But in LBVs, the star is so hot and so luminous that the outward pressure of light becomes overwhelming. It pushes against the star's outer layers with such force that it begins to lift its own atmosphere into space. Shells of gas are ejected in violent convulsions. Light curves spike and dip unpredictably. Spectrum morph from hot to cool and back again, sometimes mimicking entirely different types of stars. These outbursts are not mere hiccups. In some cases, an LBV can lose multiple solar masses of material in just a few years. That's more than our Sun will shed over its entire 10 billion year lifespan. This process not only sculpts intricate nebulae around the star but also lays the groundwork for its eventual death, by stripping away the outer hydrogen layers and revealing the hotter, denser core beneath. One of the most famous LBVs in our galaxy is Eta Carinae, which erupted in the mid-19th century so violently that it became the second brightest star in the sky, despite being 7,500 light-years away. It created a bipolar nebula called the homunculus, and released as much mass as several suns. R71, by comparison, is quieter, but perhaps only on the surface. Its 2012 eruption mimicked the same kind of explosive outburst, though it occurred in another galaxy. What unites all LBVs is their instability. Their internal structure teeters on the edge of collapse, and their surfaces are driven by turbulence, convection, and radiation in such extreme measure that no equilibrium lasts for long. And yet, in this chaos, they remain fascinating beacons for astronomers, offering clues into the late evolutionary stages of massive stars, especially those that might be on the cusp of transitioning into Wolf-Rayet stars, or preparing for core collapse supernovae. The LBV phase is fleeting, perhaps lasting only tens of thousands of years, mere moments in stellar terms. That we are able to observe R71 in this phase, especially during an active outburst, is like catching a volcano in mid-eruption that only goes off once every few thousand years. It's a rare, golden moment in observational astrophysics. R71 fits squarely into this unstable group. Over the decades, it has dimmed and brightened, shifted its spectral type, and flared up in intensity. But what makes LBVs like R71 so compelling is that their behavior defies prediction. Unlike pulsating variable stars, whose changes are cyclical and well understood, LBVs follow no rhythm. They are like firestorms in space, sudden, violent, and hard to repeat. And so, the designation of R71 as a luminous blue variable is not just a label. It's a warning. It tells astronomers, this star is dangerous. This star is transforming. This star may be dying, not in an instant, but in a series of bright, burning convulsions that may end with a supernova, or something stranger. The story of R71 would be incomplete without understanding the grand cosmic stage upon which it plays its part, the Large Magellanic Cloud, or LMC. This neighboring galaxy, visible from the southern hemisphere as a faint, hazy smear of light, is not just an accessory to the Milky Way. It is a thriving system of stars, gas, dust, and dark matter, an entire galaxy in its own right, orbiting our own like a loyal yet unpredictable satellite. The LMC is located approximately 160,000 light-years from Earth. That distance is staggering, yet small by intergalactic standards. Within this span, light takes 160 millennia to travel, which means every time we peer into the LMC, we're gazing 160,000 years into the past. That's not just a poetic notion, it's a scientific reality. The light that left R71 during its 2012 outburst began its journey during a time on Earth when early humans were painting caves and domesticating fire. That burst of light, unimpeded by the vacuum of interstellar space, is only now reaching our detectors, letting us witness a moment long past in the life of a distant giant. The Large Magellanic Cloud is a dwarf irregular galaxy, lacking the elegant spiral structure of the Milky Way, but compensating for it with raw star-forming power. Despite its smaller size, only about 1/10 the diameter of the Milky Way, it is extraordinarily active. Stellar nurseries like the Tarantula Nebula churn out massive stars by the thousands. The LMC is a cosmic furnace where hydrogen clouds collapse, ignite, and evolve into blindingly luminous stars, many of which will live short, furious lives and die in explosive finales. This galaxy is also rich in stellar anomalies, with a higher proportion of rare and extreme stars than one might expect. This may be due in part to its metallicity, or lack thereof. In astronomy, metals refer to all elements heavier than hydrogen and helium, and the LMC is relatively poor in these elements compared to the Milky Way. This seemingly small chemical difference has enormous consequences. Stars in low metallicity environments tend to evolve differently. They lose mass more slowly, burn hotter, and live faster. R71 was born in this environment, an environment where massive stars can push the limits of known physics. What makes the LMC particularly significant is its proximity. It's close enough for modern telescopes to resolve individual stars with precision, yet far enough to offer a different cosmic perspective. It's like observing a different culture in a neighboring city, similar in many ways, but fundamentally shaped by its own conditions. For astronomers, the LMC is a laboratory, a test case, a lens into how stars behave outside the conditions of our own galaxy. And R71 is one of the more extraordinary specimens in this lab. Its location in the LMC makes it a part of a broader stellar community, a collection of massive, energetic stars that includes supergiants, Wolf-Rayet stars, and other LBVs. Some of these stars are well known, like S-Doradus, the prototype for S-Dor-type variables, a subclass of LBVs, to which R71 also belongs. Others are buried in clouds of dust or waiting for their moment of eruption. But all of them, including R71, share the legacy of their galactic home, born in the high-pressure chaos of dense stellar regions, shaped by metallicity, and destined for violent ends. The LMC is not static. It is in motion, interacting gravitationally with both the Milky Way and its smaller sibling, the Small Magellanic Cloud. These interactions may trigger waves of star formation or disruptions that ripple across stellar populations. R71's own past may have been influenced by such tides, collisions, close passes, or shockwaves that helped ignite the cloud from which it formed millions of years ago. And because the LMC sits outside the plane of the Milky Way, it provides a cleaner view into the universe beyond. There's less dust in the way. Less distortion. It's a window into the broader cosmos, and through that window, we see R71, a giant flaring through the fabric of time. Among the already rare and dramatic class of luminous blue variables, R71 stands out as an anomaly, a star that doesn't just break rules, but seems to constantly rewrite them. If most LBVs are unpredictable, R71 is something stranger, a celestial chameleon, slipping between phases in a way that has puzzled astronomers for decades. Its variability isn't just a matter of brightness, it's a deep, internal shift in identity, composition, and behavior that challenges our understanding of stellar evolution. To appreciate R71's peculiarity, we need to understand what typical behavior looks like in LBVs. Most LBVs exhibit what are known as S-Doradus type variability cycles, where the star maintains a nearly constant bolometric luminosity, total energy output, but appears to brighten or dim in the visible range due to changes in temperature and radius. During these cycles, the star's outer envelope expands, causing its surface temperature to drop. This makes the star appear brighter in visible light, due to the blackbody radiation curve shifting, even though its total energy output remains the same. Later, the star contracts, heats up, and becomes fainter in the visual spectrum again. R71, however, doesn't always follow this model. In fact, it's often debated whether R71's behavior is a pure example of an S-Doradus variable, or if it represents something even more extreme. Unlike typical LBVs that exhibit regular cycles over a few years, R71's fluctuations occur over decades, and its most dramatic events defy easy classification. From Earth, astronomers have watched R71 morph through at least 3 distinct phases over the past century. In the 1970s, it experienced a significant outburst, brightening enough to be classified as an LBV. After that event, it settled into a much quieter state, appearing spectroscopically more like a post-red supergiant, cooler and more stable. This phase continued for decades, lulling observers into thinking R71 had calmed, perhaps even evolved past its LBV stage. But the 2012 eruption shattered that illusion entirely. This oscillation, between cooler, quieter phases and violent, energetic eruptions, suggests R71 may inhabit a transitional evolutionary state, straddling the line between LBV and something more terminal. Some researchers even suggest that R71's apparent calm prior to 2012 may have been deceptive, a slow gathering of energy and instability beneath the surface that finally burst forth in a spectacular release. Unlike Eta Carinae, whose outbursts were more explosive and nebula-forming, R71's transformation was more gradual, but no less profound. Adding to the mystery is the spectral variability of the star. R71's spectrum has shifted dramatically over the years, toggling between hotter B-type profiles and cooler F-type, or even A-type supergiant signatures. This isn't just cosmetic, it reflects deep physical changes in the star's outer envelope. During hotter phases, its outer layers are more compact, and it emits more in the ultraviolet. During cooler phases, its atmosphere expands, lowering the surface temperature but increasing visual brightness. Spectroscopic analysis has shown strange absorption and emission lines in R71's light, some of which have no easy explanation. These include signs of ionized metals, P Cygni profiles, indicative of stellar winds, and shifting H-alpha emissions. All of these suggest that R71 is constantly throwing off mass in inconsistent, non-spherical ways, possibly in localized eruptions or asymmetric flows. But it's not just the spectrum or brightness that changes, it's the entire structure of the star. R71 is believed to fluctuate significantly in size, especially during outburst phases. At its quietest, the star may shrink to tens of solar radii. During eruption, it likely expands to over 500 times the radius of the Sun, a mind-boggling scale that would engulf the inner planets if placed in our solar system. This expansion is not smooth or symmetrical. It's violent, chaotic, and filled with turbulence, possibly driven by opacity-driven instabilities in the star's outer envelope. There's also the matter of luminosity. While most LBVs maintain a fairly steady bolometric luminosity during their outbursts, R71's total energy output appears to have actually increased during the 2012 event. That defies expectations. It implies that something more dramatic was happening inside the star, perhaps a deep convective event or sudden core instability that pushed it momentarily beyond the theoretical Eddington limit, the point where radiation pressure would normally prevent further energy release. This anomaly, of increased total luminosity, has sparked speculation that R71 is not merely undergoing an LBV phase, but is in a pre-supernova state, a rare window into the final years or even months before core collapse. It's possible we are watching the star boil over, in stages, each one venting pressure and mass but failing to relieve the deeper instability. In this model, each outburst is not a separate event, but part of a cumulative breakdown that will eventually end in violent collapse. But even that may not capture the full complexity of R71's behavior. Some models suggest that R71 could be the product of a binary merger, a union of two massive stars in the past that now fuels its erratic evolution. The asymmetries in its mass loss, strange light echoes, and inconsistent wind profiles all hint at a past more chaotic than simple single-star models allow. In such a scenario, the instability may stem not only from internal pressure, but from a confused rotational profile, a twisted magnetic field, or uneven chemical mixing in its core. And yet, for all of this instability, R71 continues to survive. This is one of the most paradoxical traits of LBVs in general and of R71 in particular. They erupt, flare, dim, brighten, and lose massive amounts of mass, and yet they remain intact. The star's core survives each time, pushing through the layers of its own instability like a diver emerging from turbulent water. This survival is not eternal. LBVs are a phase, not a type. Eventually, the star will exhaust whatever mechanisms it has left for shedding instability. It will either transition into a Wolf-Rayet star, having lost enough of its hydrogen envelope, or it will collapse directly into a supernova, perhaps of the type Ion variety, known for interaction with dense circumstellar material expelled in previous eruptions. In the case of R71, the clock is ticking. The 2012 outburst may not be the last. Some astronomers suspect that we are witnessing the final transformations of a star approaching its limit. Every change in brightness, every shift in spectrum, is a whisper from deep within, a message encoded in stellar light, revealing not just surface changes but catastrophic internal shifts. And yet, R71 defies finality. It continues to pulse and change, showing no signs of imminent collapse, only further transformation. This alone makes it one of the most peculiar and valuable luminous blue variables ever observed. It's not just a star. It's a puzzle with cosmic consequences. A warning light. A shifting monument to everything we still don't understand about the most massive stars in the universe. Before the eruption that made it famous, R71 passed through a strange and deceptive calm, a lull that lasted not days or months, but decades. To the astronomers watching it closely, the star seemed to have settled into a subdued, almost peaceful state, betraying no hint of the violent outburst that was to come. This era, lasting from the late 1970s until just before 2012, is often described as R71's quiet phase, and it was during this time that the star adopted a spectral identity that misled many into thinking it had already completed its most turbulent transitions. In truth, it was the deep breath before a storm. In the aftermath of its earlier outburst in the 1970s, an event that had already classified R71 as a luminous blue variable, it began to fade in brightness and cool in temperature. Spectral observations from the 1980s and 1990s painted the picture of a post-outburst recovery phase. During this time, R71's surface temperature decreased significantly, settling into the range of 6,000 to 8,000 Kelvin. These values are cool for a massive star, more typical of F-type or even G-type supergiants rather than the blistering hot temperatures typical of blue variables. This cooler profile gave R71 an outward appearance more akin to a post-red supergiant, and for a while, it masqueraded as such. It exhibited a yellowish hue in the visible spectrum, broadened absorption lines characteristic of cooler stellar atmospheres, and a steady, if slightly declining, visual magnitude. Its overall luminosity remained high, still hundreds of thousands of times greater than that of the Sun, but there were no violent flares, no spectral surprises, and no evidence of mass ejection on the scale seen during its active LBV phases. To many, it seemed as though R71 had completed its LBV cycle. In the most commonly accepted model of massive star evolution, the LBV phase is a transitional episode between the main sequence and a Wolf-Rayet stage or supernova. After an LBV finishes shedding its outer hydrogen layers, it's expected to evolve into a hotter, more compact object. But R71 wasn't heating up. Instead, it cooled, expanded slightly, and quieted. It began to fit the spectral mold of a yellow hypergiant or post-RSG, suggesting that it might be entering a slow fade into obscurity, evolving toward a stable supergiant stage before eventual collapse. This interpretation, however, was misleading. Beneath its serene outer envelope, R71 was building tension. The internal processes driving its evolution, core fusion, radiation pressure, and convective instability, had not gone quiet. They had merely gone deep. The calm was superficial. Like a massive volcano lying dormant, R71 was still alive with dynamic processes far from the surface. What made this quiet phase particularly compelling to astronomers was how long it lasted, and how undramatic it appeared in all traditional measures. There were no sudden dips in brightness, no dramatic spectral shifts, and no expanding dust shells to suggest fresh mass ejection. The star seemed, if not healthy, at least stable, a rare condition for an LBV. This raised questions. Had R71 transitioned out of the LBV phase entirely? Was it now something else, a yellow hypergiant, a quiescent massive star biding its time, or perhaps the result of an unusually stable mass loss event? To make sense of it, astronomers compared historical records dating back to the early 20th century. Photographic plates from various observatories were re-examined, and light curves spanning decades were reconstructed. The data showed that R71 had undergone fluctuations in the 1930s, 1950s, and of course, the 1970s. But none of these were as energetic as the outburst that would follow in 2012. In the meantime, R71's light remained almost boring in its steadiness. Its bolometric luminosity remained roughly constant, consistent with an extended phase of radiative equilibrium. But if this was equilibrium, it was fragile. There were subtle clues that the peace was temporary. Small, gradual increases in brightness began to emerge in the late 2000s. At first, they were minor, just a few tenths of a magnitude, and easily dismissed as instrumental error or minor atmospheric variability. But repeated observations confirmed the trend. R71 was starting to brighten. Slowly. Persistently. And beneath that rise, the star's spectral profile began to shift again. Hints of emission lines crept back in. The photosphere appeared to be cooling once more, a sign that the outer envelope might be expanding. By 2011, the rate of brightening accelerated noticeably. It was then that the astronomical community began to take a second look. R71 was waking up. This realization was sobering. The decades-long lull had not been the end of R71's instability. It had been a prelude. The star hadn't transitioned out of its LBV phase, it had merely paused, preparing for an eruption more dramatic than any before. The subtlety of the calm made the explosion to come all the more astonishing. It was like watching an ocean under glass go still before the wave crashes. What makes this calm before the storm period scientifically valuable is how little we understand it. Very few LBVs are observed continuously across multiple eruptive cycles. R71's quiet phase provides a rare observational window into the internal reset that may occur between major mass loss events. It raises profound questions. What triggers an LBV outburst after such a long lull? Is it the result of processes at the stellar core, or driven by surface instabilities? Does the star need to accumulate a certain threshold of pressure, or does it fall into chaotic oscillations that occasionally breach stability? R71 didn't answer these questions during its quiet years. It only deepened them. And so the star waited, on the far edge of the galaxy, cloaked in calm, drifting in a hushed equilibrium that lulled astronomers into a false sense of security. Its light remained soft, its spectra modest, its demeanor unthreatening. Until the year that changed everything. The illusion of stillness shattered in mid-2012. After decades of relative calm, R71 began to change, and not subtly. The once stable star, long monitored and seemingly well-behaved, erupted in a brilliant crescendo of light that caught astronomers across the globe by surprise. For years, the star's slow, gentle brightening had hinted at something beneath the surface. But in 2012, that slow burn transformed into a roaring flare. It started gradually, as all great celestial dramas do. In early 2012, observatories began reporting a steady and accelerating increase in R71's visible magnitude. What had been a quiet star lingering around a visual magnitude of 10 began creeping upward toward 9. Then, almost without warning, it crossed 9 and surged toward 8.7. For a star in the Large Magellanic Cloud, 160,000 light-years away, that level of brightness was nothing short of spectacular. It marked one of the most luminous events observed in that galaxy in recent memory, and certainly the brightest flare in R71's recorded history. What made this outburst so remarkable wasn't just the scale of brightening, it was the speed and persistence of the rise. Over the course of just a few months, R71 increased its brightness by more than a full magnitude in the visual spectrum. To the naked eye, that's the difference between a faint, hard-to-detect speck and a brilliant star clearly visible through modest amateur telescopes. In astronomical terms, it was like watching a blue-white ember suddenly burst into flame. By mid-2012, the astrophysical community was fully alert. Observatories around the world, from professional institutions to serious amateurs, began redirecting their attention toward this once quiet star. Spectrographs were activated, light curves updated in real time, and new studies were commissioned with urgency. Telescopes in Chile, including those at the European Southern Observatory's Very Large Telescope, VLT, began capturing high-resolution spectra, while space-based observatories like the Hubble Space Telescope zeroed in on R71's rapidly changing profile. What they found was both stunning and confounding. R71's spectrum began to morph rapidly. Where previously the star had shown the cooler, calmer lines of a post-red supergiant, or a yellow hypergiant, its spectrum now shifted toward one resembling a cooler F-type supergiant, consistent with an enormous expansion of the star's outer envelope. Strong hydrogen emission lines returned, including pronounced H-alpha emissions with P Cygni profiles, indicating powerful stellar winds and outflowing material. These signatures told a clear story. The star was ejecting mass at a phenomenal rate, and the surrounding layers of gas were expanding outward with increasing velocity. This wasn't a gentle shedding of material. It was a storm. And it was happening in real time. Researchers quickly realized that this wasn't just another typical LBV flicker. R71 was undergoing something much more profound. The sudden increase in brightness suggested a significant change not just in surface temperature or radius, but possibly even in total energy output. This distinction is crucial. While many LBV outbursts involve a redistribution of energy across the spectrum, often appearing brighter in visible light, while maintaining constant bolometric luminosity, R71 seemed to be genuinely increasing its overall luminosity. That's a much rarer event, and one with far more dramatic implications. Theoretical models had to be reconsidered. Was this outburst the result of envelope inflation due to reaching the Eddington limit, where radiation pressure balances gravitational pull? Was the interior undergoing a helium shell flash, or some other poorly understood phase of post-main sequence evolution? Could this be an early signal of core collapse, a prelude to a supernova masquerading as an LBV eruption? At the time, these questions had no clear answers. But the data told one thing unequivocally: R71 was changing fast, and doing so in ways that broke from established patterns. In parallel with the brightening and spectral changes, observers began reporting a growing infrared excess around the star, indicating that dust was being formed and heated in the expanding circumstellar environment. This was consistent with large amounts of ejected material cooling as it traveled away from the star, likely condensing into fine dust grains. Such behavior had been observed before in other eruptive stars, but again, R71 seemed to be following its own path, displaying dust formation, mass loss, and temperature change in a complex interplay rather than a simple linear sequence. The star's effective radius, normally several hundred times that of the Sun, was estimated to have expanded even further during the peak of the eruption, possibly exceeding 500 solar radii. If placed in the center of our solar system, R71 at this size would swallow everything out to the orbit of Mars. Yet this monstrous expansion occurred without the finality of a supernova. The star had become, for a moment, a pseudo-supernova, radiating with the intensity of an explosion, but surviving its own violence. The rapid monitoring continued through late 2012. Light curves from observatories in South America, Australia, and Southern Africa converged to show a sustained plateau in brightness at magnitude 8.7, an astonishing level for a star that had sat a full magnitude dimmer for decades. The outburst seemed to stabilize into a high luminosity phase, during which the star continued shedding mass, altering its spectrum, and cooling in its outer layers. Astronomers began comparing the event with earlier outbursts of other famous LBVs, particularly AG Carinae and HD 5980, but none matched R71's behavior perfectly. There was an eerie uniqueness to the event, suggesting that either R71 was undergoing a previously unobserved mode of instability, or that it was nearing the end of its life in an unfamiliar way. Throughout it all, one aspect remained constant: the fascination and the growing sense that we were witnessing something extraordinary. A massive star, far outside our galaxy, altering its identity before our eyes, not slowly, over millennia, but quickly, over weeks and months. The kind of transformation that, once missed, might never be seen again in our lifetimes. For observers watching from Earth, R71's 2012 outburst wasn't just a scientific event, it was a performance. A cosmic monologue shouted across space and time. A massive, dying star reminding us that in the universe, stillness is often the exception and drama the rule. As the 2012 eruption of R71 unfolded, and the star's brightness climbed to astonishing levels, a peculiar question began to echo through observatories and conference halls. Had R71 just faked its own death? To an untrained eye, or even a telescope not calibrated for nuance, the outburst bore all the hallmarks of a supernova. The star had brightened rapidly by over a full magnitude, reaching a visual brightness of 8.7, becoming one of the most radiant objects in the entire Large Magellanic Cloud. It expelled massive quantities of material, shifted its spectral type, and displayed turbulent winds. The speed, the intensity, and the scale of these changes made it nearly indistinguishable from the early stages of an actual stellar explosion. But R71 didn't die. Its core remained intact. The star continued to burn. What astronomers witnessed in 2012 was something less than a supernova, but far more dramatic than a typical variable flare. It was, in many ways, a pseudo-supernova, a false alarm on a cosmic scale, mimicking the radiative output of a terminal explosion without undergoing the collapse that defines a real one. The idea of a pseudo-supernova isn't new, but R71's case forced astronomers to re-examine what it means. In a traditional core collapse supernova, a massive star runs out of fuel in its core. With no pressure to oppose gravity, the core collapses in on itself, creating a neutron star or black hole and releasing a massive explosion that obliterates the outer layers. These events are short, bright, and final. R71's outburst, however, was deceptively similar in visual magnitude but fundamentally different in mechanics. The energy wasn't coming from a collapsing core, it was coming from the surface layers, ejected in a fit of instability driven by radiation pressure, opacity changes, and convective chaos in the star's extended envelope. In other words, the light show wasn't a death knell. It was a scream of pressure and light from the outside in, not the inside out. And yet, the mimicry was convincing. Supernovae, particularly type Ion supernovae, are often associated with interaction between fast-moving stellar ejecta and slower, previously expelled material. This interaction generates strong H-alpha emissions and produces a slow-evolving light curve, sometimes spanning months or even years. R71, during and after its outburst, displayed strikingly similar emission profiles, including broad hydrogen lines, Peace Cygni profiles, and high luminosity plateaus. The thick circumstellar envelope it had built up during its prior quiet decades now served as the perfect medium for light to bounce, scatter, and resonate through, much like the echo chambers seen in real supernovae. The result was an illusion. A supernova in everything but its core. This isn't to say the event lacked danger. Quite the opposite. In some theoretical models, outbursts like R71's are warning signs. They may represent failed or incomplete core collapses, events where the instability reaches critical levels in the envelope, but the core still maintains hydrostatic balance. Alternatively, they may be pre-supernova episodes, shedding just enough mass to prepare the star for its final collapse by removing the remaining hydrogen layers. This is where the distinction between impostor and progenitor becomes essential. Astronomy has seen stars undergo supernova impostor events before. The most famous case is Eta Carinae, whose 19th century great eruption created the Homunculus Nebula and briefly made it one of the brightest stars in the sky. But Eta Carinae survived. R71, in 2012, followed a similar path, erupting with ferocity, shedding mass, and brightening dramatically, only to remain standing. The term supernova impostor was soon applied to R71's behavior, an outburst that walks and talks like a supernova, but doesn't end with stellar death. What causes these pseudo-supernova events remains an open question. Some theories propose opacity-modulated mass loss, where the intense radiation from the star builds up beneath a semi-opaque layer, like steam under a pressure cooker. When the pressure becomes too great, the envelope is ejected in a violent surge, carrying light and material into space and simulating a supernova-like appearance. Others suggest strange mode instabilities or pulsational pair instability episodes, where the internal structure of the star briefly loses equilibrium due to nuclear burning cycles or pair production in extremely hot, massive stars. These instabilities don't destroy the star outright, but they can cause explosive mass ejections that radiate like smaller-scale supernovae. In R71's case, the eruption in 2012 may have been one of these episodes, or a combination of several. It's possible the star crossed a thermal or radiative threshold that caused a runaway reaction in its outer layers, but without triggering collapse in the core. Whatever the cause, the visual outcome was a masterful impersonation of a supernova. And this has broader implications. Pseudo-supernova events complicate the task of cataloging real supernovae. For distant galaxies, where resolution is poor and timelines are short, a brightening like R71's might be misclassified as a true explosion. The light curves overlap. The spectra overlap. Even the dust echoes and post-event cooling can mimic the post-mortem glow of a supernova remnant. But the true nature of a pseudo-supernova lies in its aftermath. A real supernova leaves behind a remnant, a neutron star, black hole, or a glowing cloud of expelled material. A pseudo-supernova leaves behind the star itself, bruised but not broken, continuing its life, changed, but alive. R71 did exactly that. After its eruption, it remained luminous but quieter. It began cooling again. It showed signs of new dust shells forming around it. But it did not vanish. The core still burned. In this way, R71 joins a short but growing list of stars that simulate their own destruction, perhaps as practice, or perhaps as an unintended consequence of the laws of physics governing stars at their most extreme. These events blur the line between death and transformation, making it harder to predict when a star is truly on its last breath. Yet, they also offer a gift. They allow us to observe conditions just shy of supernova, to peer into a phase of stellar life that is normally hidden, too brief or too violent to catch in progress. In R71's brilliance, we see a threshold, a moment where the star could have died, but didn't. And in that moment, we find one of the most precious things in observational astronomy, a preview of what's to come. R71, in mimicking a supernova, reminded us that not all endings are immediate. Some come in waves. Some build slowly. Some arrive dressed in brilliance, only to reveal, in the end, that the star still has stories left to tell. By the peak of its 2012 eruption, R71 had done something truly extraordinary. It had brightened to a visual magnitude of approximately 8.7, a level of luminosity that transformed it, however briefly, into one of the brightest individual stars in the entire Large Magellanic Cloud. This was not just a statistical footnote in the annals of stellar behavior. It was a moment of cosmic theater on a grand scale. The increase in brightness was not only notable, it was historic. For comparison, R71 had typically hovered around magnitude 10 or fainter during its quiescent phases, varying subtly over years and decades but never crossing any thresholds that would draw headlines or trigger rapid observation campaigns. A rise to 8.7 may sound small, barely more than a single magnitude, but in astronomical terms, where the magnitude scale is logarithmic, that translates to an increase in brightness by more than 2.5 times. And this surge didn't happen over centuries or decades, it happened in the span of months. This brightening vaulted R71 into a new category of interest. It became, quite literally, visible to small telescopes from Earth, and bright enough to be noted in amateur astrophotography targeting the LMC. Many who had once catalogued it as a footnote in variable star lists now turned their attention toward it with urgency. Observing schedules were adjusted. international alerts circulated. R71 had become the new headline star of the southern sky. Its peak magnitude of 8.7 didn't just make it a visible beacon, it competed in brilliance with the brightest massive stars known in the LMC. For a time, it stood shoulder to shoulder with the iconic S-Doradus, after which the S-Dor type LBV class is named. And unlike S-Dor, whose variability had been relatively well documented, R71's sudden rise was far more unexpected. It disrupted decades of assumptions and revived debates about the behavior of massive stars teetering on the edge of collapse. The scale of this outburst was, in every respect, unprecedented in R71's history. Even the flare in the 1970s, its last major brightening event, had not pushed the star past a visual magnitude of 9.3. That earlier eruption was impressive, to be sure, but the 2012 event eclipsed it in luminosity, mass loss, and duration. In reaching 8.7, R71 didn't just surpass its prior peak, it smashed through it, setting a new benchmark for its class. The most significant implication of this brightening wasn't just that R71 had become more visible, but that its intrinsic luminosity, its total energy output across all wavelengths, had likely increased as well. This wasn't just a surface-level phenomenon, a cooling of the photosphere making the star visually brighter. The data, particularly from infrared and ultraviolet observations, suggested a real increase in total luminosity, potentially pushing the star beyond the classical Eddington limit, the theoretical threshold at which the force of radiation trying to blow a star apart equals the force of gravity holding it together. Such a transgression, even if temporary, is an indicator of extreme internal instability. It suggests that the radiation pressure deep within the star's interior had become strong enough to disrupt hydrostatic equilibrium, at least in the outer layers. The result was a dramatic expansion of the photosphere, a cooling of the star's surface temperature, and a powerful eruption of stellar wind, all working together to create the conditions that would generate such a monumental brightening. In fact, based on the light curves gathered during the peak, it was estimated that R71 had reached a bolometric luminosity of up to 1 million times that of the Sun. That number places it near the upper limit of what stars can emit without undergoing catastrophic collapse. Yet R71 managed to survive this episode, proof of its resilience, and perhaps a testament to just how delicate and finely balanced these massive stars truly are. One of the more haunting aspects of this historic brightening was how suddenly it happened in the astronomical sense. Stars typically evolve over thousands or millions of years. But R71 turned up the dial in just a handful of months. It's this volatility that makes LBVs so captivating. They are among the few types of stars that allow us to observe real-time changes in stellar evolution. In the immediate aftermath of the peak brightness, the star's photometric and spectroscopic profiles were monitored around the clock. Astronomers noted the emergence of new absorption features and alterations in emission lines that hinted at complex, asymmetric outflows. There were signs that dust was being formed and ejected, creating a slowly thickening shell around the star. This dust had the dual effect of absorbing some of the star's light and re-radiating it in the infrared, creating an even more complex and multi-wavelength profile. In some ways, this magnitude 8.7 moment was a kind of cosmic performance peak, a climax in a multi-act play that had been unfolding for decades. But it was not the final act. As the months passed, the star began a slow decline in brightness, but it never returned to its old baseline. It plateaued at a level significantly brighter than its pre-eruption phase, suggesting that the 2012 outburst had permanently altered the structure of the star. The eruption became a key dataset in understanding massive star behavior at the brink. R71's light curve, now etched into stellar evolution models, provides a rare, precious example of how stars may briefly flirt with the edge of destruction and then pull back, like a high-wire performer swaying on the brink, only to regain balance just in time. More than just an observational curiosity, the historic brightening of R71 has become a reference point in the study of massive star evolution, eruptive variability, and supernova impostors. It showed us that even in neighboring galaxies, stellar giants are capable of astonishing feats of luminosity, reminding us that not all brilliance ends in death. Sometimes, It's a warning, a transformation, or an act of survival. As the light from R71's 2012 eruption flooded across 160,000 light-years of cosmic void, it wasn't just the star's brightness that captivated astronomers. It was the subtle messages encrypted in its spectrum. That light, when split into its constituent wavelengths, revealed a dramatic transformation unfolding in real time. R71's spectrum, its chemical fingerprint, its voice, began to shift, echoing profound changes in the star's outer layers, atmosphere, and internal structure. What once bore the spectral hallmarks of a hot, massive, blue supergiant began to resemble something much cooler, softer, and more enigmatic, an F-type supergiant, a stellar form far removed from the ferocious heat of its luminous blue roots. Before the eruption, R71 had exhibited a spectrum typical of a mid to late B-type supergiant, that is, a star with surface temperatures between 10,000 and 20,000 Kelvin. Its light was rich in ionized helium lines, strong Balmer hydrogen emissions, and ultraviolet signatures indicative of a highly energetic photosphere. These spectral features matched expectations for a massive LBV in a quiet or post-eruptive state, radiating at high temperature but with relatively stable outer layers. But this equilibrium didn't last. As the outburst gathered momentum in mid-2012, ground and space-based spectrographs began detecting rapid and unmistakable changes. Ionized helium lines began to weaken. In their place emerged stronger neutral hydrogen features, metal absorption lines, and molecular bands that signaled a declining surface temperature. Within weeks, the entire spectral profile had pivoted away from the realm of the hot blue supergiants and into a cooler domain. The star now resembled, at least spectrally, a member of the F-class, a star with a photospheric temperature around 6,000 to 7,500 Kelvin. This was not a subtle or cosmetic change. It was a fundamental physical metamorphosis in the outer layers of the star. The cooling was likely the result of a tremendous expansion of the stellar envelope, which had ballooned outward to several hundred times the radius of the Sun. As the gas spread out, it cooled, much like the outer edge of a fire fading red as it recedes from its blue-white core. The resulting spectrum reflected this shift perfectly. R71 had become cooler, redder, and in many ways more enigmatic. The transformation brought with it a variety of fascinating spectral features. Prominent among them were P Cygni profiles and hydrogen Balmer lines, particularly H-alpha, which are classic indicators of strong stellar winds. A P Cygni profile shows both an emission and a blue-shifted absorption component in the same spectral line, suggesting material is being ejected from the star at high velocity, some of it absorbing light in our direction, and some radiating away from the star. This was a clear signal that R71 wasn't just glowing brighter, it was violently shedding mass into the space around it. In addition to these hydrogen lines, observers noted the emergence of Fe2, iron, emission lines, a signature that often appears in LBVs during eruptive phases. These lines became increasingly prominent as the eruption progressed, reinforcing the idea that R71's atmosphere had become dense and extended, allowing these lower excitation features to dominate the light. The dense outflowing wind had formed a pseudophotosphere, a layer of opaque gas beyond the true stellar surface, from which most of the star's visible light was now escaping. This shell mimicked a cooler surface, even as the star's interior continued to burn at much higher temperatures. At its most expanded phase, R71's spectrum was dominated by these cooler signatures. Analysts compared it to well-known F-type supergiants, and in some cases even to yellow hypergiants, suggesting that R71 had essentially cloaked itself in a cooler outer layer. Some even drew comparisons to S-Doradus itself, whose own outbursts had shown similar spectral migrations. Yet R71's shift appeared more extreme and perhaps more sustained, raising questions about whether it was undergoing a particularly long or unusual phase of instability. These spectral changes were not static. As months passed and the eruption evolved, so too did the features in R71's light. Emission lines strengthened, then faded. Absorption profiles widened and then narrowed. Subtle shifts in the ratios of different elements pointed to changing ionization conditions in the expanding gas shell. The star was breathing, in a sense, expanding and contracting, venting mass and then stabilizing, all while its spectral profile recorded each pulse like a seismograph. One of the most intriguing discoveries came from ultraviolet and near-infrared observations, which revealed that the outer layers of R71 had become so extended and opaque that light from deeper regions was being blocked or scattered, leading to a reddening of the visible spectrum. This reddening wasn't just from interstellar dust, it was intrinsic to the star's new outer environment. It was as though R71 had wrapped itself in a cocoon of its own making, filtering its light through veils of gas and dust expelled in the throes of its instability. This cocoon, while visually spectacular, had consequences for the star's observed luminosity and mass loss rates. The cooler spectrum implied lower surface temperatures, which in turn meant that much of the star's energy output was shifting to longer wavelengths, in the infrared. Space-based infrared telescopes detected an increasing excess in IR emission, likely from newly formed dust in the outer ejecta being heated by the radiation from the inner star. This dust further complicated the spectral analysis, as it introduced scattering and absorption features not present before. Despite these complexities, the overall picture was clear. R71's spectrum had evolved from that of a luminous blue variable into something closer to a yellow hypergiant or F-type supergiant, reflecting dramatic changes in temperature, radius, mass loss, and atmospheric composition. And all of it had occurred within months, far too short a timescale for evolutionary change in a traditional stellar model. This was no slow transformation, it was a cataclysm in slow motion, a sudden upheaval that rewrote the star's outer structure almost overnight. This spectral evolution provided crucial data not just for understanding R71 itself, but for modeling the late stages of massive star evolution in general. It demonstrated how quickly a massive star can transform, how dramatically its outer envelope can shift in temperature and density, and how profoundly these changes can affect what we see from Earth. It was a real-time view into a phase of stellar life that is often theorized but rarely witnessed. In the broader tapestry of stellar evolution, R71's spectral journey was a message from the frontier, a signal that the rules are more fluid than we imagined, that identity is mutable even for stars, and that what appears fixed in the night sky is often anything but. As the 2012 eruption of R71 surged to its peak, the star's behavior pointed toward a colossal transformation not only in brightness and spectrum but also in physical size. While most stars retain relatively stable radii throughout their evolutionary stages, R71 shattered expectations. Observational data suggested that its outer layers were expanding on a scale rarely seen in stellar astrophysics, growing so large that its radius may have ballooned to over 500 times that of the Sun. To grasp the magnitude of this change, consider what it means for a star to reach such a size. The Sun's radius is about 696,000 kilometers. Multiply that by 500, and R71's outer envelope would stretch over 348 million kilometers, or roughly out to the orbit of Mars. In simple terms, if R71 were placed at the center of our solar system, Mercury, Venus, Earth, and possibly even Mars would be engulfed within its swollen photosphere. This was no longer a star in the conventional sense. It was a cosmic balloon of gas and plasma, expanded to a volume so immense that its light took hours to travel from the core to the photosphere. The cause of this enormous expansion lies in the physics of radiation pressure and envelope instability. At the peak of its outburst, R71 appeared to have approached or temporarily exceeded the Eddington limit, the point at which the outward push of photons equals the inward pull of gravity. When a star crosses this boundary, the result is instability in the outer layers, where photons trapped inside can push out against the stellar atmosphere with enough force to cause it to swell and, in extreme cases, eject mass. But R71 didn't explode, it inflated. Its atmosphere, responding to the rising internal pressure, expanded outward at a rapid rate, becoming more diffuse and cooler as it did. The consequence of this expansion was a drop in surface temperature, which helps explain why the star's spectrum evolved to resemble an F-type supergiant. In truth, the internal core of R71 was likely still burning at millions of degrees, but the expanded envelope, acting like a massive, translucent fog, gave the appearance of a cooler, yellow-white star. The size increase wasn't merely a theoretical projection, it was supported by direct luminosity temperature radius calculations based on blackbody approximations. The Stefan-Boltzmann law, which relates the total energy radiated per unit area of a star to the fourth power of its temperature, allowed astronomers to infer the star's radius from its observed luminosity and effective surface temperature. When R71 cooled to around 6,000 to 7,000 K while simultaneously maintaining or increasing its bolometric luminosity, the only way to reconcile those numbers was with a significant increase in radius. This wasn't just an expansion, it was a structural redefinition. The star's outer atmosphere likely transitioned into a quasi-static, optically thick wind, a kind of extended, semi-stable shell of gas that hovered above the true photosphere. This pseudophotosphere dominated the visible emission, masking the hotter interior and giving R71 its spectral signature. Such shells are common in LBV eruptions and can be responsible for significant photometric and spectroscopic transformations. Meanwhile, high-resolution spectroscopic data revealed that R71's wind speeds were relatively modest, suggesting that this expansion wasn't purely an explosive event. The star wasn't launching its atmosphere into space at hypernova-like velocities. Instead, it was puffing outwards, its mass leaking into the surrounding space like steam from a boiling pot. This mode of expansion, while dramatic, was not terminal, another key distinction between R71's behavior and that of a true supernova. The massive expansion had several profound implications. First, it created a new environment around the star, a thickening circumstellar medium composed of slower winds, ionized gas, and freshly formed dust grains. This medium began to absorb and scatter the star's radiation, especially in the UV and optical bands, and re-radiated it in the infrared. Infrared observatories began picking up increasing signals from this region, showing the early stages of a dust shell formation around R71. That dust shell would eventually serve as a fossil record of this expansion, a relic of the star's most inflated and luminous state. Second, the expansion marked a significant mass loss phase, one that may have permanently altered the star's evolutionary trajectory. As the outer layers expanded and became less gravitationally bound, it became easier for R71 to shed mass through stellar winds. Estimates from this period suggested that the star might have been losing mass at rates of up to 10 to 10 solar masses per year, a staggering figure, comparable to the annual mass loss of Eta Carinae during its great eruption. Third, the radius increase added new complexity to R71's classification. Was it still a luminous blue variable? Or had it briefly morphed into a yellow hypergiant, or something even rarer, a transitional object caught in the act of redefining its spectral class entirely? The sheer size of the star during this period blurred the lines between conventional categories, forcing astronomers to reconsider what boundaries define LBVs, yellow hypergiants, and supernova impostors. But perhaps most significantly, the expansion of R71 gave scientists an unprecedented window into real-time stellar evolution. Normally, stars expand and contract over thousands or millions of years. Here, the transformation was happening over weeks and months. It was as though the star had accelerated its evolutionary clock, unfolding centuries of stellar behavior within a human lifetime. That expansion, of course, couldn't last forever. Gravity would eventually reassert control. As the outburst faded, the outer layers began to cool and fall inward, contracting slowly. But the event left behind evidence of what the star had become, if only for a moment, a bloated, unstable, luminous behemoth, nearly 500 times the size of our Sun, glowing not in peace, but in the heat of its internal turmoil. And even as the atmosphere began to contract, no one could say for sure whether R71 was done erupting, or if this was only the prelude to something even more cataclysmic. Despite all the data, despite the years of monitoring and the treasure trove of photometric, spectroscopic, and infrared observations, one question continued to haunt astronomers in the aftermath of R71's 2012 eruption: what exactly had they witnessed? Was this a textbook LBV outburst, an example of a known but extreme stellar behavior? Or was it something more unusual, something outside the familiar boundaries of current theory? The magnitude of the event alone made it suspicious. Yes, luminous blue variables are known for their instability. Yes, they can undergo brightening events that span multiple magnitudes. And yes, they can expel massive quantities of material and alter their spectra in dramatic ways. But R71 seemed to push every one of those parameters right to the limit, and then step over them. Some scientists initially classified it as a particularly strong S-Doradus type eruption, a slow brightening accompanied by cooling and envelope expansion without a corresponding increase in the star's total energy output. This would be the classical LBV pattern. The star becomes optically brighter, appears cooler due to the expanded envelope, but maintains a relatively stable bolometric luminosity. However, closer analysis complicated that neat narrative. Observational data suggested that R71's bolometric luminosity had increased as well, not just its visual magnitude. That was unusual. In fact, it flew in the face of what many believed to be the defining limits of LBV behavior. Most LBVs, even in their most intense S-Dor phases, don't significantly exceed their pre-eruption total luminosity. But R71 appeared to break this rule, suggesting either an unusually strong burst of nuclear activity, or perhaps the breakdown of hydrostatic equilibrium in parts of the envelope. The expansion wasn't simply a cosmetic phenomenon. There was real extra energy being injected into the system, enough to inflate the atmosphere and significantly brighten the star across multiple wavelengths. This detail sparked a series of debates within the astrophysical community. Was R71 still an LBV in the classical sense? Or was it evolving into something else entirely, a Wolf-Rayet precursor, or a type ion supernova impostor, or perhaps even entering the early stages of a pre-supernova instability similar to those that precede some hypernovae? Some proposed that what astronomers had seen in 2012 was not an LBV eruption at all, but rather a failed supernova, an internal collapse that did not result in destruction but instead triggered powerful surface disturbances. Others speculated about the role of binary companions, positing that mass transfer or stellar merging could have provided the extra energy needed to fuel the brightness spike. No companion star had yet been detected near R71, but the distances involved and the dusty envelope surrounding the system could have easily obscured one. Still others looked to more exotic physics. Some theorized that the event may have involved opacity-modulated ejection driven by strange mode pulsations or nonlinear radiation instabilities, mechanisms not fully understood but theorized to occur in extremely massive, luminous stars living on the edge of equilibrium. These exotic processes could have caused brief but extreme periods of envelope inflation, leading to massive and chaotic mass loss episodes without requiring core collapse. The confusion was exacerbated by the fact that no two LBV outbursts are exactly alike, and the boundary between typical and atypical remains vague. The category of luminous blue variable is broad and somewhat fuzzy, encompassing a range of behavior that often defies neat classification. For every S-Doradus or AG Carini that fits the model, there's a star like R71 that tests its limits. This diversity makes it difficult to identify outliers, because the entire category is, by nature, defined by instability. To make matters more perplexing, historical data on R71 only went back a few decades with precision. Its behavior prior to the 20th century was largely undocumented, and any long-term cycles or patterns might still be hidden. Was the 2012 eruption part of a multi-century cycle? Was it an isolated incident? Had similar events occurred before, only to fade before telescopes could capture them? In that vacuum of certainty, models were stretched. Theoretical stellar evolution simulations, which already struggled to accurately map the post-main sequence lives of massive stars, had to be retooled to accommodate R71's luminosity increase, radius expansion, and rapid spectral shift. Some models suggested the star might have passed briefly into a yellow hypergiant phase, an unstable and short-lived stage preceding either further eruptions or catastrophic collapse. But others warned that the event might be a harbinger of an imminent supernova. In certain theoretical scenarios, the most massive stars enter chaotic eruptive periods in their final years, expelling huge amounts of mass before their cores finally collapse. SN 2009 IP, for instance, had undergone a similar brightening just before its terminal explosion. Was R71 following a similar path? Or had it, as in the case of Eta Carinae, survived a major eruption and entered a new, long-lasting phase of instability? Adding to the mystery, continued monitoring after 2012 revealed that R71 had not returned to its pre-eruption state. It remained brighter, cooler, and spectrally distinct. It had not recovered its old identity. Instead, it appeared to have permanently shifted into a new equilibrium, or perhaps a temporary one, still evolving. This raised the possibility that we were watching not just a transient outburst, but a phase transition, a stellar identity shift, the kind of transformation that usually happens behind a veil of cosmic time and distance, now unfolding before our instruments. In essence, the 2012 eruption had thrown R71's evolutionary status into question. Was it a massive LBV nearing its final breaths, shedding its hydrogen envelope before collapsing? Was it transitioning into a wolf-rayet star, preparing for a different kind of supernova years or decades from now? Or was it a rare breed of massive star that defied all neat evolutionary pathways? The uncertainty became a rallying point. The mystery of R71 galvanized observational programs and theoretical studies alike. It became a case study in how nature resists categorization, how even the most studied objects in the sky can surprise us, and how the more we learn, the more layers of complexity we uncover. R71 reminded astronomers that the line between ordinary and extraordinary in the universe is often a matter of perspective. And in the end, the star's greatest contribution may not be in conforming to theory, but in challenging it. The brilliance of R71's 2012 outburst may have seized the spotlight, but it was not the star's first performance. Far from it. Long before it erupted into astronomical headlines, R71 had already established a reputation as a temperamental and elusive variable, hinting at its unstable nature through past episodes of brightening and fading. Chief among these was a notable eruption in the 1970s, an event that at the time marked R71 as a peculiar and unpredictable member of the luminous blue variable family. That earlier outburst, though far less intense than the one seen in 2012, still captured the attention of astronomers observing the Large Magellanic Cloud. Archival photometric records show that R71 brightened by more than a magnitude during the early 1970s, peaking around magnitude 9.3. For comparison, this was roughly 5 times brighter than its baseline in the decades prior, although still significantly dimmer than the 8.7 magnitude peak reached during the 2012 eruption. What was most significant about the 1970s event wasn't just the increase in brightness. It was the behavior of the star's spectrum and wind characteristics during that time. Similar to the later event, R71's spectral profile in the 1970s began to show changes consistent with cooling and mass loss. Observations noted stronger hydrogen emission lines, evolving absorption profiles, and spectral signatures that suggested a lower effective surface temperature, all signs that the star had entered a phase of extended atmospheric instability. Even then, the 1970s outburst was recognized as a departure from its prior variability. R71 had been known as a photometric variable since the mid-20th century, flickering subtly and irregularly. But this was something more, an eruptive phase, a deliberate gesture in the language of dying stars. Still, the episode eventually settled. The star faded back toward its baseline over the next few years, and its spectral features gradually returned to their hotter, pre-eruption state. For a time, the event was classified as a textbook example of S-Doradus type variability, a known behavior among LBVs. The experience of the 1970s gave astronomers a benchmark, a reference point for what R71 could do. But it also subtly misled them. When decades later the star entered its quiet phase through the late 1980s and 1990s, many came to believe that R71 might never erupt again, or that it had already exhausted its capacity for such violence. In retrospect, this was a dangerous assumption. The calm wasn't the end of the story. It was the deep breath before the plunge. The 2012 eruption shattered any illusions that R71's prior instability had been the peak of its behavior. The difference between the two events was dramatic. Whereas the 1970s eruption resulted in a relatively modest rise in visual brightness, the 2012 event was nearly an order of magnitude more luminous in total energy output. The cooling was deeper. The atmospheric expansion was greater. The mass loss rate, though difficult to measure precisely, was likely several times higher than during the 1970s. And the transformation in the star's spectrum into something resembling an F-type supergiant was without precedent in its recorded history. It's tempting to view these two eruptions as chapters in a larger narrative. Perhaps the 1970s event was a precursor, a smaller-scale instability that set the stage for something more cataclysmic decades later. Or perhaps these were independent cycles, part of a larger rhythm unique to R71, a pulsating life pattern not yet understood. Either way, the contrast between the two events offered a valuable glimpse into the range of instability that LBVs can exhibit, and the potential for a star to evolve in ways that defy prediction. The 1970s eruption also had an important consequence. It allowed astronomers to revisit archival data with new eyes. With the benefit of hindsight and modern modeling tools, researchers began to re-examine photometric and spectroscopic records from that earlier period, searching for clues. They found hints of similar envelope expansion, albeit to a lesser extent, and evidence that R71 may have expelled a smaller shell of material during that time, one that, in theory, could still be drifting in the surrounding interstellar medium. These reanalyses also raised an intriguing possibility that light echoes from the 1970s event might be visible in dust structures near the star. Though such echoes are more commonly associated with true supernovae, the concept applies equally well to any powerful luminous outburst. If the expelled light had reflected off surrounding dust clouds, it could still be detectable today with the right instruments and filters. Discovering such echoes would provide a three-dimensional map of the region around R71 and help estimate the mass and structure of older ejecta. Despite the similarities between the 1970s and 2012 events, the differences far outweighed them. The earlier eruption, in hindsight, seemed almost restrained, as if the star had only hinted at its full potential. The 2012 outburst, by contrast, was a display of raw stellar energy, nearing the upper bounds of what a star can endure without undergoing collapse. It forced astronomers to consider whether R71's behavior was evolving, growing more intense over time. Could this be a sign of accelerating instability as the star moves toward its final fate? Was R71's next eruption likely to be even more powerful, or its last? And yet, the value of the 1970s eruption remains high. It serves not only as a comparative baseline but also as a reminder that stellar history is essential to stellar future. Without the earlier event, the 2012 eruption might have seemed even more bewildering. With it, astronomers had at least a partial roadmap, one that could be used to trace how R71's physical properties had changed across decades and how its internal dynamics might be progressing toward eventual collapse. Even now, the lessons from that quieter, less explosive past echo through astrophysical studies. They emphasize the need for long-term monitoring of massive stars, the importance of patience in astronomy, and the fact that even small brightening events may carry within them the seeds of future cataclysm. R71 had erupted before, but never like this. And if history was any indication, it might do so again. The transformations that luminous blue variables undergo aren't merely optical or spectral curiosities. They are physical acts of destruction and renewal. When a star like R71 enters one of its eruptive phases, it doesn't just glow brighter or swell in size, it sheds its skin, layer by layer, releasing vast clouds of matter into the void. These outbursts are not symbolic gestures. They are literal mass loss events, some of the most extreme in the known universe short of a supernova itself. R71, during its 2012 eruption, exemplified this process in dramatic fashion. The increase in brightness and the drop in surface temperature were only part of the story. Beneath those observable changes, something more violent was happening. The star was ejecting enormous quantities of its outer envelope into space, in a stellar wind driven by intense radiation pressure, instability, and internal convulsions. In essence, the eruption was a form of self-stripping, a way for the star to relieve its own internal stress by peeling away its outer layers. This mass loss was not a gentle breeze, it was a furious storm, hurling stellar material outward at speeds of hundreds of kilometers per second. During the peak of the eruption, it is estimated that R71 may have been losing mass at a rate of 10 solar masses per year, or even more. To put that in perspective, that's equivalent to losing several Earths' worth of material every month, or the mass of the entire Earth every few days. Over the course of the eruption, the total mass lost may have rivaled the mass of Jupiter, or more. Such prodigious outflows of matter are not unique to R71. They are defining characteristics of LBVs, whose very classification hinges on this episodic but intense mass loss behavior. In fact, the term, luminous blue variable, is in part a euphemism for a massive star in crisis, struggling to maintain equilibrium against the dual forces of gravity and radiation. As the radiation pressure from within builds to unsustainable levels, the only escape is outward, an eruption, a shedding of layers, a desperate attempt to stabilize. What drives these ejections is a complex interplay of physics. Deep within the star, fusion reactions in the core generate intense outward pressure, which must be balanced by the inward pull of gravity to maintain structural stability. But in LBVs, the balance is precarious. Their envelopes are often so inflated and tenuous that they are barely gravitationally bound. A small change in temperature, a shock wave from convective turbulence, or a shift in opacity can tip the scale, and when it does, massive quantities of material can be accelerated outward. This is especially true when the star nears or exceeds the Eddington limit, the theoretical maximum luminosity a star can have before radiation pressure overwhelms gravity. When that threshold is approached, as it likely was during R71's 2012 eruption, the star becomes dynamically unstable. Photons no longer simply stream outward, they shove matter ahead of them, driving an ever-thickening wind that accelerates into space. This isn't a steady process, it's a series of convulsions, with dense shells of gas and dust being thrown off at different speeds and in various directions. Over time, these ejected shells build up into complex circumstellar environments, dense cocoons of ionized gas and interwoven dust filaments that obscure, scatter, and sometimes reprocess the star's light. Around R71, there is evidence of multiple such shells from past outbursts, expanding rings of material that may date back to the 1970s eruption and even earlier, forming a fossil record of instability in the surrounding space. Some of this material glows in the infrared, heated by the star's radiation. Some of it scatters visible light, creating halos or asymmetrical glows in high-resolution imaging. These expanding atmospheres and shells are not just passive relics. They can interact with the interstellar medium, collide with one another, or become ionized by the star's changing ultraviolet flux. In some cases, such as with Eta Carinae's homunculus nebula, the result is a visible structure, a massive double-lobed shell that testifies to a cataclysmic ejection. Though R71 has not produced anything on that scale, at least not yet, it's likely that similar structures are forming, albeit more slowly and perhaps more subtly, hidden by distance and dust. The process of shedding isn't a one-time event either. For LBVs, it is a cyclic part of their evolution. As the star sheds its hydrogen-rich envelope, it moves closer to exposing its inner, helium-rich layers. In many cases, this process transitions the star toward a wolf-rayet phase, marked by even stronger winds, higher temperatures, and an even more stripped-down structure. In that sense, every eruption is a step toward stellar rebirth, a metamorphosis from blue supergiant to the stripped core of a massive star on the verge of collapse. For R71, the 2012 eruption was likely the most significant mass loss event in its recorded history, but it may not be the last. The material it expelled now drifts away from the star, forming an evolving cocoon of dust and gas that will echo the light of that event for decades to come. Future eruptions, if they occur, may pass through or collide with that material, creating shocks, bursts of radiation, and possibly observable light echoes. What's more, the shedding of these outer layers could dramatically influence what type of supernova R71 might eventually produce. If the star continues to lose mass at this rate, it may go supernova as a type ion, where the explosion interacts violently with dense circumstellar material, creating a spectacularly bright and long-lasting light curve. Alternatively, if it manages to shed its hydrogen envelope entirely before collapse, it could produce a type IB or IB supernova, stripped of its outer identity, but still burning brightly in death. In either case, the shedding is a countdown, a measure of how much envelope remains, how long the core can continue to burn, and how near the star may be to its final breath. Every Earth mass of material ejected is a whisper of that coming end. And yet, in shedding its skin, R71 becomes more exposed, more vulnerable, and paradoxically, more luminous. It's a paradox written in fire and plasma. The more a star loses of itself, the more of its true nature we begin to see. Behind the grandeur of R71's eruptions lies a force both subtle and violent, instability, seated deep within the heart of the star. Unlike stable, middle-aged stars like our Sun, massive stars like R71 are precariously balanced on the edge of gravitational and radiative chaos. Their cores burn through fuel at a staggering pace, and the outward pressure generated from this fusion pushes relentlessly against the star's own gravity. This internal tug-of-war is never in perfect harmony, and it is this imperfect equilibrium that makes R71, and luminous blue variables like it, so profoundly unstable. At the core of R71, temperatures soar to tens of millions of degrees, where nuclear fusion reactions forge heavier elements out of lighter ones, releasing enormous energy. This energy, in the form of photons, must fight its way out from the core to the surface. But it doesn't travel unimpeded. The star's interior is dense and opaque, so the radiation pushes against surrounding particles, transferring momentum in a process that creates radiation pressure. In stars like R71, the radiation pressure is nearly as strong as gravity itself, sometimes stronger. As the balance tips even slightly, portions of the star can become unstable. The layers closest to the surface, where gravity is weakest and where the density has decreased, are especially vulnerable. If the radiation pressure momentarily exceeds the gravitational hold on those outer layers, the result is an outward surge, a swelling, an expansion, or in extreme cases, an eruption. These instabilities are often nonlinear, meaning a small internal change can cascade outward into large-scale transformations. A temporary buildup of radiation beneath the star's surface might not be released gradually. Instead, it accumulates until it finds a weak point, then breaks through with explosive force. When this happens, the outer envelope expands rapidly, cools, and forms the pseudophotosphere observed during events like R71's 2012 eruption. The instability creates a temporary new surface that's far larger and cooler than the star's original photosphere. But the forces at play are even more complicated. In these extreme stars, opacity plays a major role. Opacity is the measure of how transparent or opaque the stellar material is to radiation. In certain temperature ranges, especially in regions dominated by partial ionization of elements like iron, the opacity suddenly increases. This means radiation becomes trapped more efficiently, building up pressure beneath the surface. When the trapped radiation eventually escapes, it does so violently, contributing to the outward thrust and driving mass loss. This phenomenon, often referred to as the iron opacity bump, is one of the prime suspects in triggering LBV eruptions. It creates localized layers within the star where the balance between radiation pressure and gravity becomes especially unstable. R71, with its high luminosity and evolved structure, may have encountered precisely such a condition in the lead-up to its 2012 event. As energy accumulated near these zones, the outer layers began to shift and pulse until, finally, the accumulated energy burst through. In this way, the star becomes its own enemy. Its immense brightness is the very thing that undermines its structural integrity. The same photons that make it visible across galaxies are also responsible for tearing it apart from within. LBVs like R71 live in this contradiction, too massive to be stable, too luminous to remain still. There are other sources of instability as well. As the core evolves and fuses heavier elements, it develops layered shells of fusion, much like the layers of an onion. These layers are turbulent and convective, constantly churning and mixing. This turbulence can send ripples of disturbance outward, further destabilizing the outer envelope. Some researchers have suggested that these pulsations may even couple with radiation pressure to enhance the likelihood of eruption, especially when multiple unstable zones align. Then there is the role of strange mode instabilities, a theoretical class of stellar pulsations that may be active in stars with very high luminosity-to-mass ratios, like LBDs. These are rapid, high-order oscillations that arise due to feedback between radiation pressure and dynamic envelope response. Though not fully understood, they are thought to be uniquely dangerous, capable of growing exponentially and triggering significant mass ejection episodes. R71's behavior may well fall within this domain, suggesting that its eruptions are not only energy-driven but also dynamically unstable on short timescales. Another factor contributing to instability is metallicity, the proportion of elements heavier than helium in the star's makeup. Stars in the Large Magellanic Cloud, like R71, have a lower metallicity than those in our Milky Way. This affects the star's opacity, wind structure, and evolutionary path. Lower metallicity generally means weaker stellar winds over the star's lifetime, but it may also mean that instabilities build up more slowly, allowing more violent eruptions when they finally occur. In other words, the 2012 outburst may have been especially severe precisely because the star had retained more of its mass than a similar star in a metal-rich environment. Ultimately, the forces driving these events aren't singular. They are a symphony of instability, all playing at different scales and frequencies. Radiation pressure swells the outer layers. Opacity traps and releases energy like a ticking time bomb. Turbulent convection pulses rhythmically, nudging the envelope toward eruption. And deep within, fusion continues, layering the core with heavier elements and inching the star closer to collapse. It's a delicate dance with catastrophe. R71, like all LBDs, is a star trying to stave off its own gravitational doom through energy, pressure, and outbursts of brilliance. But every pulse of instability is a wound it cannot fully heal. Each eruption peels away mass, exposes new layers, and leaves the star more naked, more vulnerable, and one step closer to its eventual fate, whether that be as a Wolf-Rayet star, a supernova, or something even stranger. The violence of these events, then, is not random. It is scripted into the physics of massive stars. It is the result of a life lived too fast, too bright, and too close to the edge. R71's outburst in 2012 was more than just a dramatic change in brightness or spectrum. It was, at its core, a colossal act of shedding, the star literally flinging off parts of itself into space in a desperate effort to stabilize its bloated form. If R71's eruption were a human act, it would be the equivalent of violently tearing off one's own skin to cool a fever. But for a massive star perched at the brink of equilibrium, it was business as usual. A tragic norm for a luminous blue variable. This shedding wasn't symbolic or metaphorical, it was quantifiable, real, and immense. As R71 expanded to more than 500 times the radius of the Sun and its surface cooled into the range of an F-type supergiant, it began to lose mass at a rate unseen in its modern observational history. Based on models and observational fits of spectral data during the 2012 eruption, astrophysicists estimated the mass loss rate to be on the order of 10 solar masses per year, and possibly even greater during peak moments of instability. To break that down, a single solar mass is about 333,000 times the mass of Earth. So even at the conservative estimate, R71 may have been shedding material at a rate equivalent to 30 Earths every single year. At peak intensities, that number could easily climb to 50 or even 100 Earth masses per year. It's a mind-bending volume of matter. Imagine the entire Earth, a planet that took billions of years to coalesce, being vaporized and flung into space not once, but dozens of times in the span of a few months. And this mass loss wasn't composed of benign, airy hydrogen alone. It included helium, heavier elements, ionized gases, and even dust-forming compounds that would later condense in the cooling regions of the circumstellar envelope. These particles were blown outward at velocities ranging from hundreds to over 1,000 kilometers per second, accelerated by radiation pressure and turbulence within the outer envelope. The mass wasn't merely drifting away. It was being hurled with force, driven by an internal thermodynamic imperative the star could no longer contain. The mechanism behind this monstrous shedding is tied directly to R71's position near or above the Eddington limit, where the internal luminosity is strong enough to rival the gravitational pull that holds the star together. In this state, even a slight increase in brightness can tip the scale, allowing entire shells of the star's atmosphere to become gravitationally unbound. Once freed, these layers form dense winds or erupt as discrete ejecta, creating expanding shells of material that travel outward into the vacuum of the Large Magellanic Cloud. The expelled mass doesn't vanish. It forms a complex circumstellar environment, a nest of gas and dust that records the history of each violent event. Over time, this environment grows into something resembling a cocoon or shroud, veiling the star and its light. For R71, this material may have already begun shaping a dusty envelope akin to the early stages of nebulae seen around other LBVs like AG Carinae, or even the more extreme Eta Carinae. The inner edges of these shells glow with scattered starlight or infrared radiation, telling the story of the star's instability in glowing loops and arcs. The amount of mass ejected also has long-term evolutionary implications. A star like R71 likely began its life with somewhere between 40 to 60 solar masses. Over its lifetime, it has already shed a significant portion of that through line-driven winds, thermal pulses, and now, massive eruptions like the one in 2012. If the star lost even just 0.01 solar masses during the 2012 outburst alone, it would be a transformational moment in its structure, pushing it further along the pathway toward either a Wolf Rayet phase or a final supernova collapse. These numbers are not merely academic, they are predictive. The more mass R71 loses, especially from its hydrogen envelope, the more likely it becomes that the star's death will resemble a stripped envelope supernova, a Type IB or IB event, rather than the classic hydrogen-rich Type II supernova. And if R71 continues shedding mass at even a fraction of the 2012 rate, that transformation could be accelerated dramatically. Additionally, such extreme mass loss affects not only the star but also the space around it. The expanding ejecta carries angular momentum, enriched materials, and momentum that can compress the interstellar medium, triggering star formation in nearby regions of the LMC. In this way, R71 becomes not only a destroyer of itself but also a creator of future generations of stars. A cosmic paradox where death sows the seeds of birth. This process also complicates future observations. The denser the circumstellar medium becomes, the harder it will be to obtain clean optical or ultraviolet data from the star. Infrared and radio astronomy may become the primary tools to probe the mass loss history of R71, helping astronomers map the flow, structure, and composition of the shed material. Every outburst leaves behind a fingerprint, a chemical and spatial record of what the star was, what it expelled, and how it changed. R71 is not alone in its mass-shedding madness. It joins a gallery of stellar giants that have carved their fate in expelled plasma and dust. But the sheer scale of its 2012 event marked it as a mass-loss monster, a star so unstable that holding itself together was no longer viable. In its desperate act of self-preservation, it did what only the most massive stars can do, destroy part of itself to remain whole a little longer. For now, the shedding has slowed. The star has retreated from the edge. But the atmosphere around it still drifts with the relics of that violent release, swirling, glowing, and expanding ever outward, whispering the story of a star that lost dozens of Earths in a single year. In the aftermath of R71's explosive 2012 outburst, astronomers around the world found themselves grappling with a deepening question: what, exactly, is R71 becoming? As the star dimmed slightly and settled into a new, altered state, still luminous, still massive, but different, it became clear that R71 might not be merely an LBV in temporary upheaval. It might be a star in disguise, transitioning before our very eyes into something entirely new. At the forefront of these theories is the possibility that R71 is on the verge of becoming a Wolf Rayet star, or that it is inching ever closer to its final supernova death, the ultimate act in the drama of stellar evolution. Wolf Rayet WR stars are the exposed, stripped cores of once massive supergiants. These stars have lost most, if not all, of their outer hydrogen envelopes, exposing inner layers rich in helium, carbon, nitrogen, and other heavier elements produced through nuclear fusion. They are blisteringly hot, extremely luminous, and known for their ferocious stellar winds. WR stars represent a phase in which a massive star has burned through its fuel with such intensity that the layers shielding its nuclear heart are peeled away, by winds, eruptions, or both, until only the core remains. For R71, the 2012 eruption may have been a signal flare of this impending transformation. Its shedding of massive quantities of material, changes in spectral profile, and shift toward cooler, more extended configurations suggest a star that is no longer just unstable, it is evolving. If the hydrogen envelope continues to be stripped away, whether by repeated eruptions or continuous high-rate winds, then R71 may, within a few thousand years, or even decades, join the ranks of the Wolf-Rayet class. One challenge to confirming this theory lies in the observational ambiguity. R71 still displays spectral features consistent with an LBV, particularly those associated with S-Doradus type variability, and retains signs of an outer hydrogen-rich envelope. But it has become more difficult to classify. Some researchers now describe R71 as existing in an intermediate state, no longer fully LBV, not yet clearly WR. This phase could be a unique, short-lived transition, one that few stars survive long enough to exhibit clearly. Adding weight to this theory is the star's history of mass loss. WR stars don't just appear overnight, they are carved over time, sculpted by years or centuries of instability. Every time R71 sheds its outer layers, it draws closer to revealing its inner, denser self. And as that core becomes more exposed, the star will inevitably get hotter again, moving back to the blue side of the Hertzsprung-Russell diagram. It's not a reversal, it's a metamorphosis, a death spiral spiraling inward toward core collapse. That brings us to the other possibility, one that looms larger with every unstable pulse. R71 might be preparing to go supernova. Massive stars don't live quiet lives. They are born in chaos, live fast, and die violently. Once the nuclear fuel in a star's core is exhausted, it can no longer support itself against gravity. For stars of R71's size, perhaps 30 to 40 solar masses at this stage of its life, the collapse can trigger a supernova of incredible power. But the type and character of that supernova depends heavily on the star's structure at the time of death. If R71 retains most of its hydrogen envelope, it would likely explode as a Type II supernova, perhaps a Type IN, marked by interaction with the dense circumstellar material the star has expelled during previous eruptions. These explosions are spectacularly bright and long-lasting because the outward blast wave collides with the ejected shells of gas and dust, producing shock-heated emission that sustains the luminosity for months or even years. But if R71 loses most of its hydrogen before that moment, either through continued eruptions or via sustained stellar winds, it might instead become a Type IB or even Type IB supernova, with little or no hydrogen signature in the explosion's light curve or spectrum. In this case, the explosion is slightly less luminous but provides crucial insights into the final stages of massive stellar evolution and the role of mass loss in shaping stellar deaths. There is also the tantalizing, though less likely, possibility that R71 could go out as a peri-instability supernova, or a failed supernova that collapses directly into a black hole with little or no light. While these are rarer and typically associated with stars exceeding 100 solar masses, unusual cases have been known to blur the boundaries. If internal mixing or binary interaction had artificially boosted R71's core mass, some models allow for such exotic ends. But current observations lean more strongly toward the classic collapse and explosion model. Whatever the precise pathway, one thing is clear: R71 is not a stable star. Its current calm is not a return to equilibrium, but the eye of the storm, a momentary pause in a longer collapse that is still unfolding. And whether that collapse takes 10 years or 1,000, the trajectory is set. The star is exhausting its options. Its fuel is dwindling. Its envelope is thinning. The clock is ticking. The final transformation, when it comes, will likely be swift and violent. A shockwave racing outward at tens of thousands of kilometers per second. A blinding flash of light visible across the LMC. A last heartbeat measured in gamma rays and neutrinos. And in the aftermath, a supernova remnant, a pulsar, or perhaps the invisible ghost of a black hole where once a luminous blue variable roared. But until that day arrives, R71 remains a puzzle. A chameleon. A star in disguise. R71 does not exist in isolation, not just astronomically, but also within the context of stellar classification. Its behaviors, transformations, and eruptive episodes place it within a rare and enigmatic group of stars known as S-Doradus type luminous blue variables, a class named after one of the most iconic and studied stars in the Large Magellanic Cloud, S-Doradus itself. By aligning R71 with this group, astronomers gain a framework through which its instability, variability, and evolutionary significance can be better understood. But this connection also deepens the mystery, because the S-Doradus class is itself one of the most elusive and complex categories in all of astrophysics. S-Doradus type LBVs are massive, highly luminous stars that experience dramatic, often unpredictable shifts in brightness and temperature. These shifts aren't explosive in the sense of supernovae, but they are episodic and transformative, defined by periods of visual brightening and spectral softening. During their so-called outbursts, these stars appear to cool dramatically and inflate in size, shedding mass while maintaining or even increasing their overall luminosity. These phases can last months, years, or even decades. R71 exhibits all the hallmarks of this behavior. In quiescence, it shows signs of a hot, compact supergiant, or even pre-Wolf, Rayet conditions. But during outbursts, like the seismic one in 2012, it undergoes a massive shift. The star becomes cooler in temperature, shifts to an F-type spectral appearance, grows in size, and becomes significantly brighter in the visible spectrum, all without increasing its actual energy output. This is due to the formation of a pseudophotosphere, where the dense wind and expelled material temporarily act as a new surface, obscuring the hotter layers beneath. This characteristic cycle is the defining trait of the S-Doradus class. The star S-Doradus itself, after which the category is named, was the first to be identified with this behavior, having displayed significant photometric and spectral variability dating back to the early 20th century. Located in the same galaxy as R71, the Large Magellanic Cloud, S-Doradus became the prototype for an entire subclass of stars. These are not merely variable stars in the classical sense. They are dying giants, navigating the final, chaotic stages of massive star evolution. What makes this connection more than just taxonomical is the shared galactic environment. Both S-Doradus and R71 are products of the LMC's lower metallicity conditions, which influence the way their mass loss processes unfold. Stars in lower metallicity environments like the LMC typically have weaker radiation-driven winds compared to their counterparts in the Milky Way. This potentially allows them to retain more mass for longer, which could explain why S-Doradus type behavior in the LMC appears particularly pronounced. In such settings, when mass loss does occur, it tends to be episodic and violent, rather than steady and gradual. For R71, membership in the S-Doradus class is not simply a convenient label, it's a critical diagnostic. It tells astronomers that what they're witnessing is not unique, but rather a known pattern, albeit one expressed in an especially extreme form. It also suggests certain expectations. Further outbursts are not only possible, but likely. The star's mass loss history, spectral evolution, and future trajectory can all be modeled, at least in part, by drawing comparisons with other S-Dor type LBVs. But if R71 fits the mold, it also challenges it. In many ways, the 2012 outburst was too extreme, even for an S-Dor type variable. The shift in temperature, the scale of the expansion, and the mass loss rate exceeded typical expectations for the class. For this reason, some astronomers have suggested that R71 may represent a transitional example, bridging the gap between classical S-Doradus variables and the most eruptive LBVs like Eta Carinae, which experienced a full-blown, great eruption in the 1840s. Though R71's event was not on the same scale, it echoed similar mechanisms: deep instability, radiative imbalance, and a desperate ejection of mass. There is also speculation that S-Doradus type behavior may be a preparatory phase for more catastrophic outcomes. In this view, LBVs like R71 and S-Dor are not merely variable. They are stars that are actively dying, and their variability is the death spiral playing out in slow motion. Each eruption is not an anomaly, but a symptom. Each phase of cooling and mass ejection brings them closer to core collapse. Within this framework, the S-Doradus classification becomes more than a category. It becomes a warning sign. A blinking light in the stellar evolutionary sequence that signals, this star is unstable, nearing the limits of what it can endure. And in that sense, R71's inclusion in the S-Doradus class places it in the company of doomed titans, cosmic leviathans whose fates are sealed not by calm dimming, but by spectacular implosions. As astronomers continue to monitor R71 and its kin, the S-Doradus connection provides both context and caution. It tells us what to expect, but also reminds us that exceptions may be the rule. R71 may follow the classic LBV to WR to supernova pathway. Or it may surprise us with a new kind of instability, an eruption or collapse that rewrites the textbooks. For now, it stands among the stars bearing the S-Doradus name, luminous, erratic, and teetering on the edge of something final. Looking at R71 through the lens of modern observatories can give us a breathtaking glimpse into its present turmoil, but to truly understand the full arc of this star's evolution, we must turn backward, into the archives, the notebooks, the photographic plates, and the spectral logs of astronomers past. For this star, history is not just background, it's data. Because R71 has been quietly, and sometimes not so quietly, transforming for over a century. The earliest reliable observations of R71 date back to the mid-20th century, when astronomers began systematically surveying the Large Magellanic Cloud in more detail. Though it wasn't known as R71 at the time, it was flagged as a particularly luminous and unusual star. What stood out early on was not its extreme brightness, but its unsteady personality, its tendency to shift in color and magnitude, as if torn between multiple identities. These early irregularities in brightness were subtle, but frequent, and pointed toward the kind of photometric variability that would later define the LBV class. In the 1970s, R71 underwent its first well-documented eruption, and this is when it truly began to capture the attention of the astrophysical community. Between 1970 and 1977, its brightness increased from around magnitude 11 to magnitude 9.9. This two-magnitude jump in visible brightness was substantial, especially for a star previously thought to be stable on long timescales. The event was accompanied by a shift in its spectral classification, similar to what was later seen in the 2012 outburst. It cooled from a hot blue supergiant into something more akin to an early F-type star, complete with a pseudophotosphere. What followed was a gradual fading and return to quiescence, confirming that this was not a terminal supernova but rather an LBV outburst. Interestingly, the post-1970s version of R71 did not look exactly like the pre-eruption star. Even after the brightness returned to baseline, the spectral lines hinted that structural changes had occurred. Perhaps some mass had been lost, or the stellar wind profile had been altered. This eruption became the star's defining event, until 2012. But in between, R71 continued to show low-amplitude fluctuations, the kind of slow, cyclic brightening and dimming characteristic of S-Doradus type LBVs. From the 1980s through the early 2000s, long-term monitoring revealed periodic variations on timescales of several years. These cycles weren't as explosive as the 1970s eruption, but they suggested that R71 was never truly stable, just oscillating between states of marginal equilibrium. Then came a subtle change. In the late 2000s, around 2007 or 2008, observers began to detect an uptick in brightness, gradual at first, but unmistakable. The star began to brighten again, crossing magnitude 10, then 9.5. By mid-2012, it surged past magnitude 9.0, peaking near 8.7, making it one of the brightest stars in the entire Large Magellanic Cloud. And just like in the 1970s, this optical brightening came with a cooling of the spectrum and signs of a dramatically inflated stellar radius. Only this time, the outburst was more violent, more extended, and far brighter than anything on record for R71. By comparing these events, the 1970s eruption and the 2012 outburst, astronomers can begin to map patterns of behavior. Both events involve temperature drops, expansion of the outer envelope, and significant increases in visual brightness. Both were preceded by years of low-amplitude variability. And both left the star altered, with a new baseline for luminosity, wind structure, and possibly internal configuration. These repeating patterns give weight to the idea that R71 is cycling through a late evolutionary stage, perhaps oscillating its way toward core collapse. But the differences between the events are just as important. The 2012 outburst was brighter, cooler, and longer lasting than the 1970s event. The temperature dropped to nearly 6,500 K, and the radius may have extended beyond 500 solar radii, nearly double what was inferred from the earlier eruption. This suggests a deepening instability, or perhaps a critical point in the star's evolution that has been reached. Some researchers have speculated that the 2012 event wasn't just another LBV outburst. It may have been the final, massive ejection of the hydrogen envelope, a necessary step before transitioning into a Wolf-Rayet star. Going further back, indirect historical records may even suggest variability in R71 stretching into the early 20th century. Though data from this period is sparse and less precise, some old photographic plates of the LMC reveal hints of light curve anomalies that match R71's position. If confirmed, this would imply that the star has been undergoing cyclical instability for at least 100 years, if not longer, possibly even centuries. This long-term variability sets R71 apart from other LBVs. Many LBVs exhibit instability for a few decades before collapsing or transitioning into a WR phase. R71, by contrast, has been surviving through eruptions, cycling through instability with remarkable resilience. This longevity may be due to its mass, internal composition, or even rotational dynamics, all of which can affect the timing and character of outbursts. What emerges from the historical record is not a single event, but a narrative of increasing unrest. Each outburst is more intense than the last. Each quiescent phase ends sooner. The patterns point not to random variability, but to an evolutionary countdown, a slow shedding of the star's outer layers as it races toward a final, catastrophic transformation. And in that narrative, the clues from the past are vital. They don't just explain what R71 has been. They forecast what it may become. When a star like R71 undergoes a powerful eruption, the event doesn't just radiate outward in the form of light and matter. It also leaves behind ghosts of its past, imprinted on the cosmos in a form both ethereal and illuminating. These are known as light echoes, a phenomenon where the light from a luminous outburst bounces off surrounding dust clouds and arrives at Earth long after the original explosion has faded from view. In essence, it is the cosmic equivalent of hearing a thunderclap moments after seeing lightning, a delayed glimpse of a once brilliant flash, scattered and replayed across space. In the case of R71, whose violent outbursts in 1970 and especially 2012 expelled vast amounts of energy and material into the surrounding interstellar medium, the conditions are ripe for light echoes to form. The Large Magellanic Cloud, its galactic home, is rich with diffuse dust and gas, complex webs of material shaped by previous generations of stars. As the powerful light from an LBV eruption streams outward, some of it travels unimpeded directly toward Earth, giving us the first view of the event. But a fraction of that light encounters dust grains nearby, bouncing off them like a flashlight beam off a wall. These scattered photons take a longer path to reach us, delaying their arrival by months, years, or even decades, depending on their trajectory. The effect is not merely theoretical. It has been observed in other stars, most famously around Eta Carinae and the remnants of historical supernovae like SN 1987A, also located in the LMC. In these cases, light echoes have provided an invaluable second look at long-gone stellar events. With modern imaging technology, Especially from high-resolution telescopes like Hubble, astronomers can watch the echoes move, expanding outward like ripples in a cosmic pond. These glowing arcs and shelves are not remnants of matter, but reflections of light, photonic fossils that replay the eruption like a delayed video. For R71, the 2012 outburst presents one of the best opportunities to observe this phenomenon in action. The eruption was bright enough and recent enough that light echoes may still be propagating through surrounding dust clouds. While R71 is not as embedded in a dense nebula as Eta Carinae, it has shed multiple shells of material over the decades, some of which may have drifted far enough to now serve as scattering surfaces for light echoes. Detecting them, however, is not straightforward. These echoes are incredibly faint compared to the direct starlight and require deep, high-contrast imaging techniques. Observatories use difference imaging, comparing photos taken years apart, to reveal subtle changes in brightness that hint at moving light reflections. These can appear as faint, expanding arcs centered on the star or as irregular patches of glow in the surrounding sky, often only visible in certain filters, especially in the optical and near-infrared wavelengths. If successfully captured, a light echo from R71's 2012 eruption would be more than just a visual curiosity. It would allow astronomers to reconstruct the original eruption's properties in detail, even if some of that information was missed or obscured during the initial event. By analyzing the spectrum of the echoed light, scientists can essentially reobserve the outburst from a new angle, getting a second chance to extract temperature, luminosity, velocity, and even chemical composition data. It's like interviewing a witness who happened to be standing in a different location during the event, and their perspective may offer insights unavailable from the original, head-on view. Moreover, light echoes can map the dust itself, revealing the three-dimensional structure of the material around the star. As the reflected light travels outward and hits various layers and clumps of dust, it illuminates different zones over time. By tracking the movement and brightness of these echoes, astronomers can chart the geometry of R71's surrounding nebula, a critical piece of the puzzle when modeling how stars like this evolve, interact with their environments, and prepare for death. There's also an emotional beauty to the idea, the past, replaying itself in slow motion, long after the moment has passed. While the star today may seem calmer, and the violent brilliance of 2012 has faded from our direct view, its light continues to echo through space, whispering its story to whatever dust will listen. These whispers may continue for years, perhaps decades, depending on the distribution of surrounding material. And each new arc detected brings with it a fresh opportunity to learn, reflect, and deepen our understanding of this extraordinary object. Ultimately, light echoes serve as a bridge between time and space, a celestial replay button that gives us another chance to witness the drama of stellar life. For a star like R71, poised between identities and futures, every echo is a message, sent years ago, now arriving just in time to remind us. The past is not dead, and even fading light can speak. If R71 were to go supernova, the event would be nothing short of extraordinary, not just because of its proximity in cosmic terms, nestled within the neighboring Large Magellanic Cloud, but because of the complex, layered life the star has led. This is not a simple star at the end of its fuse. It is a living, seething contradiction, cloaked in past eruptions, surrounded by unstable winds, and shedding its identity in bursts of brilliance. Any supernova it produces would not be clean or straightforward. It would be violent, drawn out, and confusing, a cosmic fireworks display shrouded in layers of old smoke. The exact type of supernova R71 would produce depends heavily on how much of its outer envelope it has lost by the time its core collapses. Currently, R71 retains a significant, though thinned, hydrogen-rich atmosphere. If it continues to shed material, either slowly through winds or suddenly through another LBV outburst, it could end up with very little hydrogen left. But if it explodes before that point, or if the envelope remains loosely bound and still present, the resulting supernova will carry the unmistakable fingerprints of hydrogen interaction. That scenario would place R71 in the camp of type Ion supernovae. Type Ion supernovae, the N stands for narrow lines, are among the most dramatic and long-lived types. What defines them is not the initial explosion itself, but the interaction between the supernova shockwave and the dense circumstellar material, CSM, that the star expelled in the years or decades prior to death. This interaction can last weeks, months, or even years, producing a sustained glow far brighter and more complex than typical supernovae. The light curves of type Ion events can rise and fall multiple times, depending on how clumpy or asymmetric the CSM is. These explosions often feature narrow hydrogen emission lines in their spectra, produced as the ejecta plows into the dense shells of material that were once part of the star's outer layers. This matches R71's profile disturbingly well. Its 2012 eruption flung out vast quantities of mass, and it has likely undergone multiple such ejections over the past century. Surrounding the star is a minefield of slow-moving gas, dust, and stellar wind fragments, exactly the kind of chaotic medium a supernova shockwave would slam into. If R71 were to collapse in this state, we would likely observe bright, prolonged emission, strong in hydrogen lines, with possible infrared rebrightening from heated dust and complex variations in spectral features as different shells are encountered. But if the star continues to shed mass over the next few decades, it may lose so much of its hydrogen that only a thin outer layer remains. In that case, the explosion would more likely resemble a type IIb supernova. These are transitional events, beginning with hydrogen signatures that quickly fade, replaced by helium features. Type IIb supernovae are thought to originate from stars that have mostly, but not completely, lost their hydrogen envelopes, either through winds or mass transfer in binary systems. Although no confirmed companion has been detected for R71, the binary scenario is not out of the question. Many massive stars form in binaries, and interactions can strip mass more effectively than winds or eruptions alone. The light curve of a type IIb event is usually more compact than that of a type Ion. The brightness peaks and fades within weeks, and the spectrum evolves rapidly. But despite being less visually spectacular, type IIb supernovae offer deep insights into the internal structure of stars like R71. Their quick spectral evolution allows scientists to probe layers that were hidden during the star's life: helium zones, oxygen-rich cores, even traces of carbon and neon fusion. There's also a third, less likely but still fascinating possibility. If R71 manages to completely lose its hydrogen and helium layers, either through extreme wind loss or additional, massive LBV eruptions, it could explode as a type IB or type IC supernova, events that leave little to no trace of the star's outer identity. These types are more commonly associated with Wolf-Rayet progenitors, which R71 might eventually become. But such a transformation would likely require tens of thousands more years or some external stripping mechanism, making this path more speculative than immediate. Yet there's one final, ominous outcome: the silent collapse. Some massive stars, especially those in the 30 to 40 solar mass range, are thought to be at risk of undergoing failed supernovae, where the core collapses directly into a black hole without a brilliant explosion. In such cases, the outer layers may fall inward too quickly for a shockwave to propagate, and the star may simply vanish, perhaps with only a brief flash in infrared or neutrinos, detectable only to specialized observatories. Would R71 suffer such a fate? Probably not. Its instability, mass loss history, and current luminosity suggest a more extended death. The star is not collapsing in on itself without resistance. It is fighting back, shedding layers and keeping pressure in balance. For now. But the longer it walks this line, the more unpredictable its final collapse becomes. If it does explode, the result will be shaped not only by its core structure but by the legacy of every layer it has lost, and every echo it has cast into space. What we can be sure of is this: the universe is watching. R71 is one of the most intensely monitored stars in the LMC. When it finally does collapse, whether next year or in 1,000, it will be observed across the entire electromagnetic spectrum. Neutrino detectors, X-ray telescopes, radio arrays, and gravitational wave observatories will all be poised to catch the moment. It will be a rare cosmic event, a front-row seat to a dying star's final breath, unfolding not in a distant galaxy, but in our celestial neighborhood. In a galaxy full of ancient light and explosive death, R71 stands out not just for its brilliance or volatility, but for something more understated: its survival. Amidst the ruins of other massive stars that lived fast and died young, R71 persists, defying expectation, evading collapse, and outliving many of its stellar peers. For a star of its mass, this endurance is rare, and it paints the portrait of an object in slow-motion peril, holding itself together just long enough to remind us that even in the universe, survival is sometimes a story of sheer defiance. To appreciate the scale of this survival, consider R71's basic statistics. It began life likely with a mass of 40 to 60 times that of the Sun, an amount that by cosmic standards almost guarantees a short, tumultuous lifespan. The most massive stars, those in this weight class, typically burn through their nuclear fuel in a matter of a few million years. Unlike smaller stars that live comfortably for billions of years, these stellar behemoths exhaust their resources quickly, their immense gravity balanced by equally immense radiation pressure, the whole system a precarious dance on the edge of stability. Many of our 71 stellar siblings, born in the same generation within the star-forming regions of the Large Magellanic Cloud, are already gone. Their deaths are written across the sky in supernova remnants, neutron stars, and possibly even black holes, invisible but felt through gravitational tug. Some left behind intricate nebulae, circular knots of gas, X-ray hot plasma, or expanding shells of shockwave-lit debris. These are the normal fates for stars of R71's kind. In some ways, collapse is not a tragedy, it's the expected endgame of high mass and high energy. But R71 has, somehow, delayed that finale. Part of this delay can be attributed to its peculiar evolutionary track. Unlike stars that blaze through a single, straight path, main sequence, red supergiant collapse, R71 has taken a more circuitous route, moving through multiple transitional phases. It has passed through blue supergiant stages, possibly dipped into a post-red supergiant phase, and re-emerged as a luminous blue variable, its instability manifesting in eruptions rather than explosions. Each transition has bought it time. Each outburst may have vented just enough pressure to prevent catastrophic collapse, much like a valve releasing steam before the engine blows. It's as if R71 learned how to bleed off danger slowly, flaring not as a final act, but as a means of continuation. The 1970s eruption gave it a reprieve. The 2012 outburst was another stall. These events appear violent to us, but in the language of stars, they may be signs of survival strategies, desperate rebalancing maneuvers in the face of gravitational doom. This resilience is all the more impressive given the harshness of the LMC environment. Though it is a satellite galaxy, the LMC is far from serene. It's active, dynamic, and historically rich in stellar collisions, shock fronts, and ionized gas regions. Supernova 1987A occurred here, along with a host of other stellar cataclysms. R71's neighborhood is littered with the relics of destroyed stars. That it remains among them, burning steadily, though not calmly, is remarkable. More than just surviving, R71 is also still learning to adapt. Its mass is gradually declining through persistent winds and eruptions. It may now be hovering around 30 to 35 solar masses, a significant reduction from its original heft. This makes it lighter, more maneuverable, in a sense, less likely to collapse immediately, but still far too massive to escape an eventual death by gravitational implosion. For now, though, it teeters on that edge. It burns, it pulses, it radiates, but it does not fall. And therein lies the paradox. R71 is clearly dying, yet it does not die. Its every eruption hints at instability. Its spectral changes scream of inner chaos. But collapse, the terminal event all these signs seem to herald, has not come. It's as if the star were aware, somehow, that it has more to do, more to show. And so it holds on. This kind of stellar perseverance is invaluable to astronomers. In R71, we have a front-row view of a massive star navigating the final, most unstable leg of its evolution without yet detonating into supernova. It gives researchers time to study, time to model, time to prepare. It's an astronomical anomaly, yes, but it's also a living textbook, each new observation a fresh chapter in the study of stellar life and death. And perhaps that is why it captivates so much attention. Not because it has already exploded, but because it hasn't. Because R71 is still hanging on in a state of elegant ruin, its brilliance undiminished even as it teeters closer to collapse. Each day it survives is one more day we get to learn from it. One more day it defies gravity with radiation. One more day the universe gives us a window into a rare moment of delay between life and death. But time, even for stars, is not infinite. When R71 erupted in 2012, the explosion of interest from Earth was nearly as intense as the star's own outburst. Though 160,000 light-years away, its dramatic increase in brightness made it an immediate target for some of the most powerful telescopes on, and above, our planet. This wasn't just an opportunity, it was a cosmic alert. A rare and volatile luminous blue variable in the midst of a dramatic transformation had just switched into high gear. And Earth's observatories, both orbiting and terrestrial, turned their collective gaze to capture every photon. Foremost among the instruments watching R71 was the Hubble Space Telescope. Floating beyond Earth's atmosphere, Hubble offered an unobstructed view into the star's light, free from atmospheric distortion and scattering. Even before the eruption, Hubble had studied R71 during calmer phases, providing high-resolution imaging of its surroundings and narrowband photometry that revealed the early hints of variability. But in 2012, Hubble became essential. Its imaging helped resolve the complex dust structures forming around the star, illuminated by the outburst, and its spectroscopy allowed astronomers to parse the changing makeup of the star's outer layers. Hubble's spectrographs, particularly the Space Telescope Imaging Spectrograph, STEAS, enabled researchers to track the shifting absorption lines and emission features in exquisite detail. As R71's spectrum transitioned from hot to cooler configurations, moving toward an F-type supergiant profile, the absorption lines of neutral metals and the Balmer series of hydrogen became increasingly prominent. These changes weren't just cosmetic. They hinted at a transformation in the star's outer temperature, wind velocity, and radius, all critical diagnostics of the eruption's energy. But Hubble was far from alone. On the ground, the Very Large Telescope, VLT, array in Chile, operated by the European Southern Observatory, was a primary contributor to monitoring the outburst. Perched high in the Atacama Desert, where the skies are among the clearest on Earth, the VLT's adaptive optics and high-resolution instruments, such as UVS, ultraviolet and visual Echelle spectrograph, and X-shooter, allowed astronomers to dissect R71's light across a wide range of wavelengths, from ultraviolet to near-infrared. This multispectral data was vital for tracking the energy distribution of the outburst, and for examining how dust in the immediate environment responded to the sudden spike in radiation. The VLT's detailed spectroscopy also revealed multiple velocity components in R71's wind structure. These hinted at a layered ejection event, where newer, faster-moving material was slamming into older shells previously expelled in quieter episodes. This dynamic created complex emission features, including Peace Cygni profiles, which are characteristic of expanding envelopes and stellar winds. The presence of such features confirmed that the outburst wasn't just a surface flare-up. It was a full-body event, likely involving deep interior instability. Elsewhere in the world, other major observatories joined the campaign. The Southern African Large Telescope, SALT, contributed key photometric and spectroscopic data during the rise to peak brightness. In Hawaii, telescopes atop Mauna Kea, including the Keck Observatory and Subaru Telescope, captured complementary spectra and narrowband imaging. These instruments helped resolve structural features in the surrounding circumstellar material and confirmed that the pseudophotosphere had grown to hundreds of solar radii in extent. Smaller observatories also played their part. In an era of collaborative astrophysics, many semi-professional and university-based telescopes in the Southern Hemisphere contributed continuous light curve data, allowing astronomers to maintain unbroken coverage of R71's brightness fluctuations. This photometric monitoring was crucial for building a timeline of the event, tracking when the brightening began, how rapidly it progressed, how long it held, and when the slow decline began. Even infrared observatories, such as the now-retired Spitzer Space Telescope, contributed data. Though less sensitive to the central star's output, Spitzer helped examine thermal emission from dust grains heated by the outburst. This allowed researchers to infer dust composition, grain size distribution, and the presence of newly formed dust shells, evidence that the eruption had not only emitted radiation, but physically altered the star's immediate surroundings by reshaping and possibly creating new dust structures. In addition to direct observations, a rich body of archival data became invaluable during and after the event. Astronomers combed through decades of spectral records, Hubble imaging, and light curves from ground-based surveys like OGLE, optical gravitational lensing experiment, to create a broader narrative of R71's behavior leading up to 2012. By stitching together this timeline, they were able to model the star's internal instability and predict what might come next. Throughout this intense period of observation, R71 also became a touchstone in theoretical modeling circles. Observational data from Hubble, the VLT, and others were plugged into simulations to test models of radiation-driven mass loss, pseudo-photosphere formation, and envelope inflation. Each dataset refined the next, and R71 emerged not just as an object of study, but as a case study, one that would be cited in dozens of papers exploring massive star evolution, the LBV phase, and supernova progenitor identification. But perhaps what is most remarkable is how global the response was. R71's outbursts mobilized telescopes across the planet and in space, from the Atacama to Mauna Kea, from orbit to observatory domes. This worldwide effort was driven by the understanding that events like this are rare and fleeting. To miss even a few weeks of data might mean losing a critical phase in the eruption, a missed puzzle piece that could take decades to replace. And so the star, burning in a satellite galaxy, became for a time a focal point of Earth's attention. Night after night, astronomers gathered its light, broke it into spectra, catalogued its changes, and waited. In that sense, R71 became a performer on the largest stage imaginable, under surveillance not out of fear or curiosity alone, but out of profound scientific reverence. This was a chance to watch a transformation in real time, a lesson in physics delivered in light. Massive stars live fast and die young, but they don't go quietly. In the final phases of their lives, they undergo violent, unpredictable changes that challenge every model astrophysics has to offer. Among these titanic objects, luminous blue variables like R71 occupy a special place. They are rare, erratic, and caught in the briefest yet most telling chapter of a star's evolution. That's why stars like R71 are more than just distant points of light. They are cosmic laboratories, living demonstrations of physics under conditions impossible to replicate on Earth. They show us what happens when mass, pressure, radiation, and instability collide at incomprehensible scales. To understand why LBVs are so scientifically valuable, we have to look at where they stand in stellar life cycles. These stars don't begin their lives as LBVs, they evolve into them. A star like R71 may have started as an O-type main sequence star, burning hydrogen in its core at blistering temperatures, with a mass tens of times that of the Sun. As it aged, it ran through its core fuel quickly, evolving into a supergiant and beginning the process of burning heavier elements, helium, carbon, oxygen. But at a certain point, rather than transitioning smoothly into a red supergiant, or a Wolf-Rayet star, the evolutionary path splintered. The star grew unstable. Its outer layers began to swell and pulse. Its winds grew erratic and dense. And so it entered the LBV phase, a transitional identity caught between youth and death. This is where the laboratory metaphor becomes most accurate. LBVs are stars on the brink, their cores trying desperately to hold together while their envelopes push outward. This tension creates environments where fundamental physical processes reach extremes. Radiation pressure, for example, becomes more than just a balancing act. It becomes the dominant force, capable of lifting entire layers of stellar material away from the core. The star becomes what's known as Eddington Limited, where its luminosity reaches the threshold at which the outward pressure of radiation matches the inward pull of gravity. At or near this limit, even a small internal disturbance can trigger a major event, like the outburst R71 experienced in 2012. Studying LBVs lets astronomers test these delicate balances. Theoretical predictions about how massive stars shed mass, inflate their envelopes, and alter their surface composition can be compared against real, time-resolved data from stars like R71. Spectroscopic changes during eruptions give insight into opacity, ionization states, and wind velocities. Changes in brightness tell us about pulsation mechanisms and pseudophotosphere formation. Even the timing and shape of light curves offer clues about the internal physics driving these transformations. LBVs are also critical for understanding how mass loss shapes a star's fate. A star's final death, whether it goes supernova, collapses into a black hole, or fades into a neutron star, depends heavily on how much mass it retains in its final moments. LBVs are one of the most extreme examples of mass loss engines in the universe. Their winds are dense and often clumpy, capable of removing several Earth masses of material per year. These ejections sculpt the circumstellar medium and may determine the kind of supernova the star eventually produces. By observing R71 and others, scientists can refine their models of mass loss rates, wind asymmetries, and envelope stripping, which in turn influence predictions about the mass thresholds required for various end states. And it's not just about the individual star. The material expelled by LBVs becomes part of the galactic ecosystem. The chemical enrichment of galaxies is heavily influenced by massive stars like R71, which return not only hydrogen and helium, but also carbon, nitrogen, and oxygen, the essential elements of life. LBVs, through their powerful outbursts, contribute disproportionately to this recycling process, pushing enriched material into interstellar space where it may one day form new stars, planets, or even biological precursors. In that way, these unstable stars are paradoxically creators as well as destroyers, bridging the gap between generations of stellar life. LBVs also help us study phenomena that are otherwise only accessible in much more distant, or rare contexts. For example, many superluminous supernovae, those far brighter than typical core collapse events, may be connected to LBV-like progenitors that explode while still surrounded by massive, recently ejected shells. R71 provides a local, non-terminal analog to such conditions. It allows astronomers to observe the precursors to these cosmic fireworks in slow motion, over years or decades, rather than being limited to brief glimpses of distant, transient events. Moreover, LBVs force us to confront the limitations of current stellar evolution models. Traditional Hertzsprung, Russell diagrams don't easily accommodate the looping, backtracking behavior of stars like R71. Theoretical predictions for how and when massive stars should explode often fail to anticipate the extreme variability and prolonged stability LBVs demonstrate. Observations of R71 have directly challenged assumptions about the timing of envelope loss, the thresholds for collapse, and the expected brightness and temperature evolution of massive stars. Every time R71 defies prediction, it improves the model. There's also the human aspect. For astronomers, LBVs like R71 are living stories, stars caught mid-sentence in their narrative. Unlike stars that have already exploded or stars too stable to change meaningfully within a human lifetime, LBVs evolve before our eyes. They make astronomy feel personal, immediate. One year a telescope catches them in quiet contemplation, the next, in violent eruption. They are unpredictable, chaotic, but real. Their light reaches us in pulses of warning, as if to say, "I am changing. Pay attention." And we do. Because what LBVs teach us isn't confined to textbooks or research papers. They expand our understanding of time, of transformation, of fragility. They show us that even stars, the symbols of permanence in our skies, can have crises, transitions, and rebirths. And in doing so, they reflect something profound about the universe, that the edge of destruction is also the edge of creation, and the stars that live on that edge are not merely objects, they are phenomena. R71, in all its luminous instability, is one of the best laboratories we have for studying this edge. It may die tomorrow or 1,000 years from now. But until then, it will continue to burn, erupt, evolve, and teach. Though the fireworks of 2012 have faded into memory, R71 has not returned to its former self, not entirely. It remains a luminous presence in the Large Magellanic Cloud, a glowing sentinel among the lesser stars, still extraordinary, still changing. While the peak of its outburst has long passed, the star has entered a kind of simmering afterglow, quieter in magnitude but no less intriguing in its behavior. It's as though the star, having screamed once in desperation, now whispers secrets through the subtle undulations of its light. Post-2012, astronomers continued to monitor R71 obsessively. What they found was not a star slipping into stillness, but one undergoing a complex and uneven decline, a slow, asymmetrical descent from a climactic eruption. Its brightness has gradually decreased from its historic peak of visual magnitude 8.7, retreating down into the low tens. Yet it still shines more brilliantly than it did before the eruption, suggesting that its outer layers remain inflated, its surface cooler than it once was, and its pseudophotosphere not yet fully contracted. This transitional state has lasted over a decade, and during that time, observers have noted continued spectral variability. R71 no longer exhibits the extreme spectral features of a fully erupted LBV in crisis, but its absorption lines have not fully returned to those seen in pre-outburst phases either. Elements like iron and titanium still show strong, narrow features in the visual and near-UV bands, indicating the presence of a dense, slowly moving outer atmosphere. These signatures, while less dramatic than those during the eruption, remain consistent with a star that is still radiatively inflated, still wearing a veil of ejected material. Further supporting this, infrared observations reveal an enduring glow from circumstellar dust, likely heated by the energy of the eruption and subsequent stellar radiation. Some of this dust may have been newly formed in the ejected material, coalescing as the gases cooled. This thermal emission persists, suggesting that the shell is still dense enough, and close enough, to be thermally responsive to the star's energy output. In essence, the light and heat from R71 are still catching up with the very material it expelled, illuminating the aftermath in slow motion. Meanwhile, intermittent variability in brightness continues. Not on the scale of the 2012 event, but in gentle, rolling waves. Small fluctuations in visual magnitude, perhaps half a tenth to a few tenths, have been observed in some seasons, indicating ongoing internal instability. These micro-variations might be the result of pulsational behavior, where different layers of the star expand and contract slightly out of phase, altering the observable radius and temperature on timescales of weeks to months. These are the star's new rhythms, quieter than before, but still speaking. In the ultraviolet, space-based observatories have noted a decrease in high-energy emissions, consistent with a cooling outer layer. The UV flux has dropped from its outburst peak, and line emissions associated with hot wind features, like those of C4 and C4, have weakened, indicating a reduced mass loss rate compared to the height of the eruption. However, these features haven't disappeared entirely. R71's wind remains active, albeit less chaotic. It's as if the star, once blasting material into space with reckless force, is now exhaling more slowly, its breath still thick with dust and ionized gas. Crucially, despite this deceleration, the star has not reverted to the exact configuration it had before the eruption. Its effective temperature remains lower than pre-2012 levels, still placing it in the range of late A or early F-type supergiants, a cooler state that suggests the outer envelope has not fully retracted. This means that R71 is not just recovering, it's redefining itself, possibly preparing for the next phase in its journey. Whether that phase leads to further LBV activity, a Wolf-Rayet transition, or a terminal collapse remains to be seen. The duration of this post-eruption plateau is itself revealing. It tells us that the event was not a transient flare but a profound structural reconfiguration of the star. This is the long tail of a violent process, and it underscores how even seemingly singular stellar events can have decade-long consequences, reshaping the atmosphere, the wind, and the star's observable profile in ways that require patience and persistent observation to understand. Astronomers are, of course, still watching. Instruments like the VLT, Hubble, and newer observatories such as JWST continue to return to R71 for follow-up measurements. The next outburst, if one comes, will be even more closely scrutinized. But until then, this quieter phase is far from uninteresting. It is the interlude after a scream, the pause in a symphony before the next movement begins. For astrophysicists, this is the opportunity to model, to compare predictions with observations, and to examine how a star recovers, or fails to recover, from instability of this magnitude. More broadly, this ongoing transformation challenges the sharp boundaries between stellar stages. R71 shows us that transitions are not always clean, and that the identity of a star is not a fixed point on a diagram, but a blurring of states, a continuum of change governed by physics that often outpaces our understanding. In this liminal period, R71 is neither the star it once was nor the one it will become. It is a monument in transition, quiet, glowing, and still full of stories yet untold. Around R71, the space is not empty, it is alive with motion, structure, and memory. The star's long, unstable history has left behind a surrounding veil of materials shaped by powerful stellar winds and episodic eruptions, a shell of dust and gas that acts as both curtain and stage. This material does more than just scatter light, it tells a tale. It records the star's outbursts, its convulsions, its temperamental pulses. And now, in the aftermath of its historic 2012 eruption, that environment is more active and more enigmatic than ever before. R71, like other luminous blue variables, is governed by winds that are not gentle breezes, but relentless torrents of mass propelled outward by radiation pressure. In its quieter phases, the star emits continuous, dense stellar winds that push particles outward at speeds of hundreds of kilometers per second. These winds carry with them elements forged in the stellar interior: hydrogen, helium, and increasingly heavier materials like nitrogen and oxygen, as the star progresses through its late nuclear fusion cycles. Over time, these winds sculpt an extended atmosphere, a halo of enriched plasma that surrounds the star, glowing in the UV and soft X-ray spectrum. But wind is only part of the picture. During major outbursts, like the one in 2012, R71 ejects mass not as a slow leak, but as a sudden, massive surge. These episodic mass loss events drive shockwaves into the surrounding medium, compressing previously expelled material and often cooling rapidly enough to allow for the condensation of dust grains. And it is this dust, not the wind alone, that forms the veils and clouds now orbiting R71, a dusty cocoon that both reveals and conceals. Dust in this context is not the kind found in your home. These are microscopic, crystalline particles of silicates, carbon compounds, and other refractory materials, often no more than a micron across. But en masse, they are significant. They scatter starlight, absorb high-energy photons, and re-emit it in the infrared, creating an observable signature that astrophysicists can trace. After the 2012 eruption, infrared observations revealed that R71 was not just brightening optically, but also warming up its surrounding dust, a sign that new material had been ejected and was now interacting with the starlight. The structure of this dusty environment is not uniform. Models and spectral data suggest that R71's dust shell is clumpy and asymmetric, shaped by uneven mass loss and possibly even magnetic fields or rotation. Some regions may contain thick knots of material, while others are more diffuse. This uneven distribution creates directional variability in how the star appears from Earth, depending on our line of sight and how the dust shifts or disperses. In certain bands of the infrared spectrum, the star may appear brighter or dimmer purely because of these intervening clouds. These dust shells also act as light filters and time capsules. They dim the star's visual output, redden its color, and delay light through scattering, creating conditions where light echoes of past eruptions might still be observable. In fact, some researchers have explored whether echoes from R71's earlier eruptions, including the 1970s event, might still be visible by tracing reflected light off distant clumps of surrounding dust. Such observations could provide historical records, indirect glimpses into events we never directly observed. Meanwhile, R71's winds continue to reshape this environment. The current mass loss rate, while reduced from its outburst peak, is still substantial, estimated at roughly 10 to 10 solar masses per year. These winds push outward into the dust shell, possibly creating a multi-layered structure, with faster, newer winds catching up to older, slower material. This interaction zone may generate internal shocks, heating localized regions and creating variable emission features in both optical and radio bands. These wind-dust interactions can cause short-term photometric variability and produce distinct emission lines detectable with high-resolution spectroscopy. There's even speculation about dust regeneration. As the ejected material cools and expands, the density and temperature might drop to a point where molecules can form again, CO, and others, that serve as building blocks for new dust grains. This cycle of ejection, cooling, and reformation makes R71's surroundings a dynamic, evolving envelope rather than a static shell. What's also fascinating is that this dusty shroud doesn't just obscure R71, it enhances its mystery. It makes it harder to see the exact nature of the star's photosphere, yes, but in doing so, it forces astronomers to decode it through indirect light, to interpret its whispers instead of its shouts. By analyzing absorption lines altered by intervening dust, or observing infrared echoes of past flares, scientists can reverse engineer the conditions that produce these effects. The dust becomes a lens through which the star is studied, not just a veil. This dusty environment also primes R71 for a particularly spectacular supernova display, should it collapse while still wrapped in its dusty cloak. In such an event, the shockwave would blast through the circumstellar medium, energizing dust and gas, producing bright, extended emission features and possibly giving rise to a long-duration supernova light curve, especially if it becomes a type ion event. The presence of all this material doesn't just influence how we see R71 today, it will influence how the universe sees it when it dies. But for now, the winds blow. The dust glows. R71, still breathing and bleeding light, remains half hidden and half revealed in a haze of its own making. Its secrets drift in the surrounding cloud, waiting to be decoded by infrared detectors, scattered back toward Earth by dust grains orbiting in slow arcs. The star is a fire in a fog, brilliant, smothered, and utterly fascinating. To understand R71 is to understand a much larger story, one that encompasses the lives and deaths of the most massive stars in the cosmos. These stellar titans are not just brighter or heavier than stars like our Sun, they live in an entirely different register of existence, burning hotter, evolving faster, and dying more spectacularly. And luminous blue variables like R71 represent a rare and volatile stage in this drama, the final act before collapse or detonation, when a star's internal structure becomes unbalanced and unstable, teetering on the edge of its own gravity. Massive stars, those born with more than about 20 times the mass of the Sun, live short, furious lives. They spend their youth on the main sequence, fusing hydrogen into helium at breakneck speed. This stage may last only a few million years, but in that time, they pour out enormous amounts of energy, carving out cavities in surrounding space with ultraviolet radiation and fast stellar winds. As their cores exhaust hydrogen, they begin fusing heavier elements in rapid succession: helium, carbon, oxygen, neon, magnesium, and finally silicon, producing increasingly less energy at each stage. The end result is an iron core, the dead end of nuclear fusion, where adding more mass actually consumes energy instead of releasing it. What happens next depends on many factors: the star's total mass, its mass loss history, its metallicity, and the configuration of its outer layers. Some massive stars evolve into red supergiants, cool but immense in size. Others shed their outer envelopes and become Wolf-Rayet stars, hot and compact with stripped hydrogen layers. And then there are the luminous blue variables, stars like R71 caught in a state of flux, too unstable to settle, too massive to shrink, oscillating between brightness and silence in a desperate effort to delay the inevitable. In many models, the LBV phase is a brief transitional stage, lasting perhaps 10,000 to 100,000 years at most, cosmically speaking, a blink of an eye. During this time, the star undergoes episodes of extreme mass loss, shedding material at rates far exceeding those of normal stellar winds. These eruptions can eject several solar masses of material, building up a circumstellar shell that will later become crucial in shaping the star's explosive finale. Eventually, when the core fuses its last usable fuel and iron begins to accumulate, the star can no longer support itself against gravitational collapse. The core implodes in milliseconds, and what follows can vary dramatically. If the collapse generates enough outward pressure, a core collapse supernova occurs, one of the brightest events in the universe. If not, the star may collapse directly into a black hole, with little to no outward sign, becoming one of the most elusive and final objects in existence. LBVs are strong candidates for type Ion supernovae, a classification characterized by narrow hydrogen emission lines and prolonged light curves. These features arise when the supernova shockwave crashes into the dense shell of material expelled during the star's LBV eruptions. In this sense, the LBV phase does more than foreshadow the explosion, it prepares the stage for its spectacle, shaping how the death of the star will appear from Earth. But some LBVs may never go supernova. It's possible that in some cases, especially for stars near the lower mass limit for this phase, the star evolves instead into a Wolf-Rayet star after shedding enough mass. These stars are hydrogen-stripped, hot, and compact, and they, too, are destined to die, but in different flavors of supernovae, such as type IB or IC, which lack hydrogen lines in their spectra. Whether R71 follows that path remains an open question, but its recent behavior suggests it may still have significant hydrogen left, making a type Ion outcome more likely if it explodes soon. The most massive stars, on the other hand, may end in instability supernovae, rare and incredibly powerful explosions that completely unbind the star, leaving no remnant behind, not even a neutron star or black hole. This occurs when the core becomes hot enough to generate electron-positron pairs, leading to a sudden drop in pressure and runaway collapse. These events are theorized to be more common in the early universe, but they remain a tantalizing possibility for the most extreme LBVs if their masses remain sufficiently high. And then there is the silent killer, direct collapse into a black hole. In this scenario, no brilliant supernova lights the sky. The star simply disappears, its core folding in on itself, its outer layers perhaps falling in after it. This may be the fate of stars that have lost too much mass too quickly, or stars with extremely high mass cores that prevent shock revival during collapse. Detecting such deaths is difficult. They might be discovered only by the sudden disappearance of a known star, or perhaps by brief gamma-ray flashes if any jets form during collapse. What makes R71 so fascinating in this context is that it could go down almost any of these paths. It is a star caught mid-evolution, and its erratic behavior opens the door to all these possibilities. Its mass loss could accelerate, stripping it down to a Wolf-Rayet core. It could hold on to its hydrogen and die in a dramatic type Ion explosion. Or it could linger long enough to collapse silently, its final act invisible to all but the most sensitive instruments. We don't know, and that is what makes observing R71 so urgent. This uncertainty isn't just academic. Understanding the fates of massive stars is critical to understanding how galaxies evolve, how elements are distributed, and how compact objects like neutron stars and black holes form. Massive stars shape their environments through feedback, by ionizing gas, seeding space with heavy elements, and sending shockwaves through interstellar clouds that can trigger new star formation. Their deaths, in turn, are responsible for many of the high-energy phenomena observed across the cosmos: gamma-ray bursts, supernova remnants, gravitational wave events. R71 is one piece in that puzzle, a living laboratory still spiraling toward its unknown end. In its light, we see the destiny of many stars. In its instability, we glimpse the universal tension between energy and entropy, between creation and collapse. To study R71 is to study fate itself, not just of one star, but of every massive star, of every brilliant beacon destined to burn fast, die young, and leave behind echoes that ripple across space and time. R71, even in its quiet moments, pulses with meaning. It is not just a star. We can think of it as a cosmic memoir, written in eruptions and spectral lines, in outbursts and quiet luminosity. From this distant giant, orbiting in the neighboring Large Magellanic Cloud, we draw more than data. We draw insight into the nature of change, into the violence that precedes transformation, and into the restless heartbeats of the universe's most massive children. What R71 teaches us first and foremost is that instability is not an anomaly, it is an intrinsic feature of life for massive stars. These stars are born with so much mass, and burn their fuel so quickly, that equilibrium is never more than temporary. Their luminosity presses against the very boundaries of what gravity can hold together. In this state, even small perturbations, slight shifts in temperature, opacity, or composition, can trigger drastic consequences, eruptions, mass loss, or even the rearrangement of the star's outer layers. R71 demonstrates that instability can be cyclical and drawn out, not just a prelude to death but a defining phase of stellar evolution. Its 2012 outburst, for example, was not the end, but a violent rebirth, a release of pressure that may have extended the star's life by allowing it to shed unstable outer layers. That event, which mimicked the light curve of a supernova without the destruction, exemplifies a kind of cosmic purging, an organism overwhelmed by its own internal energy, flaring to rid itself of excess. There's something almost organic in the behavior of such stars. They regulate themselves not with precision, but with bursts of chaos. R71 reminds us that nature does not always seek calm, it often thrives on transformation, even when the process is destructive. We also learn about timing. R71's variability doesn't occur on neat, periodic intervals. It isn't a metronome, it's a symphony with pauses and crescendos, false starts and unexpected climaxes. Sometimes it rests in a quiet, cool phase for decades. Sometimes, without warning, it brightens and changes temperature and begins throwing mass into space like a runaway forge. This kind of behavior challenges our traditional models of stellar evolution, which often assumes smooth, linear progressions. R71 shows us that stars can loop backward in the Hertzsprung-Russell diagram, revisit earlier stages, and express identities that seem contradictory. A star can be hot and cool in the same decade, bright and dim in successive years. It teaches us to expect fluidity, not just between spectral types, but between phases we once thought distinct. On a deeper level, R71 teaches us about cosmic violence, not as an act of destruction alone, but as an engine of creation. The material it sheds in eruptions doesn't vanish. It becomes part of the interstellar medium. Dust forms from those gases, and that dust may one day seed new stars, or collect into planets. The energy released helps illuminate nearby clouds, triggers star formation, and reshapes the environment around it. R71 shows us that massive stars are not just luminous, they are architects of their own surroundings, and their instability is how they sculpt space. They carve their history into the void with waves of force. At the same time, R71 reflects something poignant about the nature of death in the universe. It's not always instantaneous. It can be slow, staggered, and uneven. It can involve repeated attempts to stabilize, to shed what can't be sustained. In this way, R71 echoes processes we see all across nature, even in our own biology, ecosystems, and civilizations. Destruction is rarely sudden. More often, it is a slow unraveling, punctuated by moments of intensity. It may take millennia for R71 to die, and it may suffer many convulsions before its core finally collapses. But in each moment, it reveals a bit more about how stars live, how they struggle, and how they end. There is also a philosophical resonance here. R71 is located in another galaxy, far outside our own, and yet it becomes deeply personal to us. We track its brightness, parse its light, theorize its future. We devote time, technology, and imagination to a star we will never touch or truly know. And why? Because stars like R71 tell us what the universe is made of, not just physically, but dynamically, emotionally, metaphysically. They show us a cosmos in motion, full of processes that are violent, unpredictable, and yet patterned. In that sense, R71 is more than a subject of study. It's a mirror of the universe's temperament, brilliant, unstable, evolving, and destined to leave something behind. It also reminds us how fragile observation can be. Had its 2012 outburst happened just a few decades earlier, we might not have caught it in such detail. It was the right moment, with the right telescopes, and the right focus of attention. It emphasizes how important it is to watch, to wait, to record even what seems quiet. Because the cosmos doesn't announce its changes in advance, it simply changes. And if we're watching, we might catch a star like R71 in mid-transformation and learn more in that moment than from years of theory. And finally, R71 teaches us humility. Despite everything we've learned, from light curves, from spectral data, from computer models, we still cannot predict exactly when it will erupt next, or if it will explode, or how it will die. It's a reminder that the universe is still full of questions without answers, and that's what makes it worth exploring. Every time R71 surprises us, it reaffirms the value of curiosity and the necessity of awe. It proves that even in this age of advanced science and precision instruments, mystery still exists, and it still burns in the hearts of stars. R71 does not rage like a dying warrior, nor does it fade like a flickering candle. It exists somewhere between these metaphors, a celestial phantom, burning not with violence, but with sorrowful intensity. A star suspended in transition, still luminous, still powerful, but not what it once was, and never again what it will be. It drifts now through the final, uncharted passages of stellar evolution, casting off pieces of itself into the void, each one a message, each one a memory. It is not dead, but it is dying. And in that slow undoing, it tells a story that is far bigger than itself. We call it a luminous blue variable, but its identity slips through our definitions. It has been a blue supergiant, a red pretender, a dust-shrouded beacon, and now a golden, spectral presence, cooler than before, but somehow brighter in meaning. R71 has moods. It has changed its temperature and size, its wind patterns and brightness, its very shape in the sky. And it will change again. This star, thousands of times more massive than our Sun, floats in the night like a restless spirit, too vast to hold steady, too brilliant to disappear quietly. And so we keep watching it, not just because it's spectacular, though it is, but because it speaks. It speaks to the cycles of instability and rebirth, of transformation and surrender. It is a lesson in impermanence, written not in ink but in hydrogen and helium, in iron and dust. Every photon it emits has traveled for 160,000 years to reach our eyes, carrying with it a message that even the strongest things in the universe must, at some point, let go. Perhaps it will explode. Perhaps it will collapse. Perhaps, in some subtle future outburst, it will vanish from our skies and become something else entirely, a supernova remnant, a neutron star, or a black hole. But until then, it endures. Not in stillness, but in performance. Every shimmer is a confession. Every spectral shift is a sigh. R71 teaches us that stars, like stories, are never truly finished. They echo, evolve, and haunt the darkness long after their light has dimmed. This is the beauty of the cosmos, not its stability, but its movement. Not its order, but its capacity for change. R71 reminds us that creation and destruction are not opposites, but phases of the same cosmic heartbeat. It is a dying giant, yes, but also a living mystery, still unfolding before us, still reshaping what we know about the life cycles of stars. So we mark its changes, and we wait. Not because we hope for its end, but because we are privileged to witness its journey. To see, in real time, the shedding of a star's identity. And in that slow unraveling, those brilliant flashes, those surging winds, those dimming sighs, we are reminded of something universal. Even stars can have moods. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.